Good morning. While we're waiting for the participant to join in this room, we will be display the Uni Italia Indonesia video and followed by the safety induction room. It will take around 12 minutes. Thank you.
Selamat datang di MIPA Universitas Gajah Mada. Saat ini Anda sedang berada di Auditorium lantai 7 gedung perkuliahan S1 MIPA Universitas Gajah Mada. Ruangan ini dilengkapi dengan dua buah pintu utama di sisi belakang yang berfungsi sebagai pintu masuk dan keluar ruangan. 4 buah pintu darurat yang berada di kanan dan kiri Anda. Fasilitas kamar kecil berada di kanan dan kiri bagian depan gedung ini. Sebelah kanan untuk toilet putri dan sebelah kiri untuk toilet putra. Untuk menuju toilet, Anda dapat keluar melalui pintu kanan dan kiri ruangan ini. Kemudian, berjalan menuju ke arah belakang podium. Ruangan ini dilengkapi dengan fasilitas keadaan darurat berupa alat pemadam api ringan atau APAR yang terletak di samping luar pintu ruangan, di kanan, kiri, dan belakang, serta smoke detector yang tertanam di langit-langit ruangan. Titik kumpul terdekat berada di halaman depan gedung ini, digunakan untuk berkumpul ketika terjadi keadaan darurat. Bapak Ibu dapat berjalan dengan menuruni tangga hingga lantai dasar dan keluar gedung. Gedung ini belum memiliki fasilitas musala. Apabila Anda ingin beribadah, silakan berjalan keluar melalui pintu utama dan turun melalui tangga menuju Masjid Baitul Ilmi yang terletak di depan gedung ini. Hari ini kami tidak melakukan simulasi atau latihan keselamatan. Apabila Anda mendengar bunyi alarm atau lonceng secara terus-menerus, maka itu adalah tanda dari keadaan darurat yang sebenarnya. Anda kami mohon untuk tidak panik, tetap tenang, segera keluar melalui pintu keluar terdekat. Bagi yang menggunakan alas dengan hak tinggi, harap dilepas, turun melalui tangga, tidak menggunakan lift. Utamakan perempuan hamil, lansia, dan difabel. Ikuti arah jalur evakuasi menuju titik kumpul utama di halaman depan gedung ini. Kemudian, ikutilah arahan lebih lanjut dari petugas kami. Semua standar keselamatan dan semua langkah evakuasi keselamatan telah sesuai dengan peraturan yang berlaku. Keamanan dan keselamatan Anda adalah tanggung jawab kami. Terima kasih.
Good morning, buongiorno, sugeng enjing. His Excellency the Ambassador of Italy to Indonesia, Mr. Benedetto Lateri, the Honorable Rector of Universitas Gajah Mada, represented by Vice Rector for Research, Business Development and Partnership, Mr. Ignacio Susatyo Wijoyo, the Honorable Chairperson of National Research and Innovation Agency, Bapak Laksana Trihandoko, the Honorable Dean of Fakulty Mathematics and Science, Universitas Gajah Mada, Mr. Kuatriana, and the Vice Dean's Faculty of Mathematics and Science. The speaker for the scientific seminar of this morning, the Honorable Mr. Roberto Carniel, Scientific Attaché at the Italian Embassy, the Honorable Mr. Romero Sinaga from Uni Italia, Indonesia, and distinguished guests, ladies and gentlemen. We also extend a warm welcome to the Meteorological, Climatological and Geophysical Agency Region Yogyakarta, the Institute for Research and Technology Development of Geological Disaster, Director of Directorate of Business Development and Incubation, Director of Alumni Partnership and International Affairs, and the Director of Research Universitas Gajah Mada. Assalamualaikum warahmatullahi wabarakatuh. On behalf of the organizer, we would like to extend a warm and express our gratitude for participating in the Italian Research Day celebration, Giornata della Ricerca, Italiana nel Mondo, with a scientific seminar and roundtable discussion at Auditorium Fakulty Mathematics and Science, Universitas Gajah Mada, 7th floor undergraduate building. I am Hanani Wijayanti Putri, acting as the master of the ceremony of this event today. And to begin with, allow me to read the agenda for our event today. First of all is opening event. Second, singing the national anthem. Third, welcoming speech and opening remarks from Dean of Faculty Mathematics and Science Universitas Gadjah Mada. Distinguished speech from Rector of Universitas Gadjah Mada. Distinguished speech from Chairman of BRIN. Distinguished speech from Ambassador of Italy. 7. Souvenir handover and documentation. 8. Presentation from Uni Italia Indonesia. 9. Scientific seminar. 10. Break session. 11. Roundtable discussion. 12. Conclusion. And the last, closing. The honorable distinguished guests, ladies and gentlemen, let us all rise for a singing the national anthem, starting with the national anthem of Italy, Il Canto degli Italiani, and followed by the national anthem of Indonesia, Indonesia Raya. Ladies and gentlemen, please stand up. Please have a seat. Next agenda is welcoming speech and opening remarks. As the host and fully support this event, I would like to invite Dean of Faculty Mathematics and Science Universitas Gadjah Mada, Mr. Kuatriana. To Professor Kuat, time is yours.
Assalamualaikum warahmatullahi wabarakatuh. Distinguished guests, colleagues, and friends, on behalf of the Fakulty of Mathematics and Natural Sciences, Universitas Gadjah Mada, it is my pleasure to welcome you all to the Italian Research Day in this room. We have the honor of welcoming the Rector of Universitas Gadjah Mada, represented by the Vice Rector for Research Business Development Partnership, Bapak Ignatius Satya Wijoyo. Terima kasih Pak. The Ambassador of the Italia, Dr. Benedetto Letri, the Italian Ambassador to Indonesia, and the Chairman of the National Research and Innovation Agency of Badan Riset Nasional BRIN, Bapak Dr. Laksana Trihandoko. Thank you for your willingness to give speech and gracing us with our presence. The Faculty of Mathematics and Natural Sciences, in collaboration with the Italian Embassy in Jakarta, has organized a scientific seminar and roundtable discussion as a part of the Italian Research Day. So the theme of the today's event is data reduction and machine learning applied to geophysical time series. We are privileged to have experts in this field who will share their knowledge and insight of these fascinating topics. So we are also pleased to announce that a scientific seminar will be held today with Dr. Roberto as a keynote speaker. Thank you very much for coming and giving lecture today. And hopefully we are eager to expand our collaboration with research and industry in Italy in the future. So we hope that this collaboration will continue to grow, especially in education, research, and other scientific events. Therefore, we ask for help for Italian Embassy in facilitating us to wider cooperation in the future. Jadi Bapak Ibu, kami lihat dari lembaga seperti BMKG dan juga Pak Ibu Guru, kami sampaikan sekalian promosi ini dalam bahasa Indonesia, sorry. Fakultas MIPA selalu dikonotasikan dengan ilmu-ilmu yang jauh dari kebutuhan masyarakat. Dikonotasikan sebagai bidang yang dikembangkan sangat fundamental, sangat tidak menarik. Kami sedang mengarah kepada pembenahan isu itu sehingga kami di Fakultas MIPA ada 8 program studi sarjana. Yang lainnya sudah sangat terkenal seperti ilmu komputer, yang sekarang paling baru ilmu aktuaria itu persaingannya sangat tinggi sekali. Kemudian ada statistik, mathematics, chemistry. Nah, ada elektronika dan instrumentasi, ada lagi enggak ya? Kemudian 2 program studi yang selalu kita dengar sepi peminat, yang itu berada di Departemen Fisika. Ada program studi fisika dan program studi geofisika. Ini yang kami akan memberikan informasi kepada Bapak Ibu sekalian, khususnya Bapak Ibu Kepala Sekolah dan Bapak Ibu Guru yang hadir pada kesempatan hari ini. Di luar sudah sebagian kecil yang bisa kita tampilkan di produk-produk inovasi yang didorong oleh Pak Wakil Rektor, yang berasal dari program studi geofisika dan juga dari program studi elektronika instrumentasi. Tentu bukan sekedar itu, kami ingin mengangkat isu terkait dengan geofisika. Ini kita sedang membuat TikTok Bapak Ibu untuk memberikan informasi yang lebih baik. Masuk geofisika nggak dikenal gitu loh. Ya, jadi ini sayang sekali. alumni-alumni kita banyak di oil company, banyak menguasai industri-industri yang sangat sangat high impact gitu. Tetapi tidak dikenal sama sekali di masyarakat. Apalagi fisika. Fisika juga, ini mohon nyun titip pada Bapak Ibu guru dan kepala sekolah untuk menyampaikan bahwa mungkin kami juga punya andil kesalahan karena pembelajaran fisika di SMA barangkali kurang inovatif, mohon maaf. Mengapa? Karena kalau udah bicara fisika ya bandul matematis gitu, kata Prof. Jasi. Atau gerak peluru gitu, sekedar itu. Padahal kita tahu Bapak Ibu inovasi-inovasi di prodi fisika juga tidak kalah seru, khususnya di UGM. Mungkin ini sudah pamer juga. Jinus salah satunya yang kita kembangkan itu adalah dari program studi fisika. Nah, kalau fisika tidak saya bahas lagi karena itu sudah sebetulnya tinggal memulai saja untuk beritahukan pada masyarakat luas. Tadi kami juga laporan sekilas kepada Pak Wakil Rektor bahwa dengan kemampuan kita yang saat ini saja di prodi fisika kami bisa jualan jasa ke industri manufaktur terbesar di Jerman. Nilainya memang belum besar, tapi estimasi tahun ini sekitar 100.000 euro. Ya bagi kami itu lumayan besar. Hanya jualan jasa, melakukan enhancement performance dari chip device yang diproduksi di Jerman, dikirim ke fisika, dan kami melakukan suatu treatment. Nah, treatmentnya apa ini masuk dalam NDA, Non-Disclosure Agreement, yang tidak boleh kita bocorkan. Nah, kemudian hasilnya nanti akan dikembalikan ke Jerman, dan kita berharap di hampir semua produk yang nanti disematkan pada produk-produk Apple itu ada kontribusi dari prodi fisika. Kira-kira seperti itu. Ini real. Kita tepuk tangan saya kira. Ya. Jadi kami ingin membalikkan informasi bahwa tidak seperti yang dibayangkan di masyarakat umum. Sugeng rawuh Pak Direktorat Penelitian. Jadi kira-kira seperti itu, nanti kami akan mencoba untuk melakukan komunikasi dan juga semacam marketing gitu ke SMA, ke sekolah-sekolah, ke guru-guru, kalau perlu nanti kita bikin event yang baik begitu, mungkin dikemas dalam bentuk Innovation Day atau apa gitu ya Pak. Nah, kalau yang lain saya tidak bahas karena ini sudah persaingannya sangat ketat gitu. Persaingan sangat ketat, terutama untuk ilmu komputer dan juga elektronika instrumentasi. Bahkan kami sekarang punya 3 IUP, International Undergraduate Program, yang persaingannya juga sekarang lumayan ketat juga, jadi mungkin karena masih murah. Nah, ini permasalahan di MIPA seperti itu Pak, biar sekarang laporan ini suruh menaikkan SPP pada nggak mau. Gitu. Oke, ini untuk informasi dari kami, khususnya untuk 2 program studi yang sepi peminat. Kalau Bapak Ibu kalau lihat di TikTok itu mudah sekali cari. Dan banyak sekali orang membahas itu. Tapi kita pastikan bahwa sepi tetapi dahsyat, kira-kira seperti itu ya. In closing, I would like to express my sincere appreciation to all the participants, speakers, and also organizer, Pak Wiwit, who have made this event possible. We hope that this event will serve a platform for fruitful discussion and collaboration between our institution and scientific community. Thank you very much. Assalamualaikum warahmatullahi wabarakatuh.
Thank you to Mr. Kuat. And the next agenda, we will have a speech from the honorable guest of this event. This speech from Rector of Universitas Gadjah Mada, represented by Vice Rector for Research, Business Development and Partnership, to Mr. Ignacio Susatyo Wijoyo. Please come to the stage.
Selamat pagi, good morning, Assalamualaikum warahmatullahi wabarakatuh. Salam sejahtera buat kita semua, Om Swastiastu, Namo Buddhaya, salam kebajikan. I am honored to greet you all to the Italian Research Day at Universitas Gadjah Mada, Faculty of Mathematics and Natural Science. Italian Research Day promotes research and innovation in Italy and Indonesia. This event is hosted by Faculty of Mathematics and Natural Science at Universitas Gadjah Mada and the Italian Embassy in Jakarta for Indonesia. And an Italian researcher, professor, student. The event includes keynotes, panel discussion, exhibit, and networking. It is joy to welcome Mr. Benedetto Latteri, the Italian ambassador to Indonesia. We appreciate your presence and dedication to strengthening connection between Italy and Indonesia through innovation and research. Dr. Laksana Trihandoko, Chairman of the Indonesian Research and Innovation Agency, we call it BRIN, and Professor Kuat Triana, Dean of the Faculty of MIPA, Mr. Roberto, Pak Wiwit, are also with us today. We appreciate your support for this event and your commitment to advising Indonesia research and innovation. This event provides a forum for Indonesian and Italian researchers, academics, students, and professionals to exchange ideas, share knowledge, investigate opportunity for collaboration. It is a chance for us to learn from one another and work together to resolve some of the most pressing issues facing our societies today. As a higher education institution, UGM is committed to fostering research and innovation in variety of disciplines. We believe that through research and innovation, we can contribute to the growth of and improvement of our society and humanity as a whole. We hope that this event will inspire and motivate all of us to continue pursuing excellence in research and innovation and to collaborate for better future for all. Again, I'd like to extend a warm welcome to the Italian researchers to Italian Research Day at Fakultas MIPA UGM, and I hope you all have a productive and pleasurable time. Thank you very much. Wassalamualaikum warahmatullahi wabarakatuh. Thank you.
Thank you, Mr. Ignatius. Next speech is from Chairperson of National Research and Innovation Agency, Mr. Laksana Trihandoko. Mr. Laksana Trihandoko will be deliver his speech by the video.
Terima kasih, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Selamat pagi, salam sehat, salam sejahtera untuk kita semua. Salam, Om Swastiastu, Namo Buddhaya, salam kebajikan. Very good morning, ladies and gentlemen. The Ambassador of Italy for Indonesia, His Excellency Benedetto Latteri, Honorable Rector of Gadjah Mada University, Professor Ova Emilia, distinguished speakers, my colleague in Jakarta, and particular Professor Kuat, and all participants. It is a great pleasure for me, on behalf of National Research and Innovation Agency, or shortly BRIN, to deliver a short remark on today's Italian Research Day in Yogyakarta. Unfortunately, I could not attend this event in person, but I am personally very glad to know that some of you have great interest on time series data, in particular related to geophysical data. As a huge archaeological country, Indonesia is not only rich of biodiversity, either from terrestrial or our water territory, but we are also very rich of natural disaster, unfortunately. In particular, geological disaster like erupting volcano, earthquake, and also its subsequent tsunami. On the other hand, we have also faced very challenging climate that is very difficult to predict in most of our region. So this is the main reason why so far Green has a long-term plan to develop integrated data acquisition system coming from our underwater, ground surface, and also atmosphere up to ionosphere using the unmanned field station with various sensors and also remote sensing satellite constellation to generate high-resolution satellite images. So this initiative is very important for our country to acquire comprehensive data from our environment, including some geological dynamics in an almost real-time way throughout the country. So we are expecting in the near future to deploy a few hundreds of unmanned field stations across the country, including coastal areas along watersheds in some main rivers and also big lakes. So once this kind of system is running fully, hopefully, maybe within few years, by 2025, hopefully, except the satellite remote sensing satellite constellation, of course. Because for the remote sensing satellite constellation, we expect to complete all of the satellites, in total 18 satellites within 10 years. So after having complete unmanned field station across Indonesia, we can collect very comprehensive time series data for the first time in the world, in particular for equatorial region like Indonesia. So taking this opportunity, I would like to invite all of the scientists across Indonesia and also our potential global partners to join our collaboration using the next coming data from our unmanned field stations. I think this would conclude my opening remarks. I hope all participants enjoy the event, have nice discussion with Italian experts coming in this event. So thank you very much. Wassalamualaikum warahmatullahi wabarakatuh. Om Santi Santi Santi.
The next speech will be delivered by Italian Ambassador to Indonesia, as Mr. Benedetto Latteri is currently engaged in other embassy activities and will be provide his remarks by the video.
Let me start acknowledging the Rector of University Gajah Mada, Dr. Ova Emilia, Chairman of BRIN, Dr. Laksana Triandoko, Dean of the Faculty of Mathematics and Natural Sciences, Dr. Uat Tuyana, honorable authorities, ladies and gentlemen, good afternoon. I'm very honored to open this Day of Italian Research in the World here in Indonesia, made possible by the reopening of the position of scientific attaché in our embassy after many years. The role of scientific attaché is to promote the bilateral scientific collaboration between Italy and Indonesia in all scientific fields, with possible industrial, technological, commercial, and social positive achievement. A number of events are organized by all Italian scientific attaché in the world around April 15, the date of birth of Leonardo da Vinci, in 1452. Leonardo is one of the symbols of Italian genius. He was able to apply his knowledge and skill in the most disparate fields and art and science, being a scientist, philosopher, architect, painter, sculptor, a master of drawing, anatomist, botanist, musician, and engineer. Between our two countries, natural hazards must play a special role in scientific collaboration. Indonesia is unfortunately exposed to almost all the natural hazards we can think of. Natural hazards are also intertwined with human activities and climate change. And for these reasons, they request policies and actions by the government. This is why we decided to organize this Italian Research Day in the world here in Yogyakarta, where not only we have the Universitas Gadjah Mada, but which is one of the most prestigious universities in Indonesia and the host of this event today, but also where the important task of monitoring the Merapi volcano takes place at the Geological Disaster Technology Research and Development Center. I'm sure this day will be fruitful and rewarding for all of us. I wish you success, and I look forward to learning about the outcomes of this today event. Thank you very much. Terima kasih.
Move to the next agenda is souvenir handover and photo session. I would like to invite the Honorable Vice Rector for Research, Business Development and Partnership of Universitas Gadjah Mada, Mr. Ignatius Susatyo Wijoyo, the Honorable Dean of Faculty Mathematics and Science Universitas Gadjah Mada, Professor Kuatriana, MSI. In the top stage. The souvenir is given from Faculty of Mathematics and Natural Science to Universitas Gadjah Mada. Thank you. Please stay to the stage. Before after this, we have a documentation to also we invite the speaker, Mr. Roberto Carniel and Mr. Romero Sinaga to come to the stage to take picture together. And also our Director of Universitas Gadjah Mada invitation. to take picture with all distinguished guests, please can move to this section, and please the photographer can take from in front of the guests. Also, this event is a stream on our YouTube channel, Faculty Mathematics and Science. Please stand up to all distinguished guests. Okay, 1, 2, 3, smile. Okay, once again, with a Yogyakarta. 1, 2, 3, stay. Okay, the last, it's one? Okay. Thank you so much to all of the distinguished guests. Please have a seat. The honorable distinguished guests, ladies and gentlemen, next agenda is presentation from Uni Italia Indonesia with the theme Study in Italy, an immersive experience. With the honorable speaker, Mr. Romero Sinaga. To Mr. Romero Sinaga, please come to the stage and start your presentation.
Oke, selamat pagi Bapak Ibu semuanya. Buongiorno a tutti. So, can I present with mixed languages, Bahasa or English? Which one you prefer? Okay. I'm very comfortable with mixed languages, so I can present my presentations with mixed Bahasa and English. So everyone, welcome. So we are coming from Unitalia Indonesia as the Education Department in the Embassy of Italy in Jakarta. So the title of this presentation is an immersive experience. Why immersive? Because we would like to present you an immersive experience to study in Italy. So next slide, please. Okay, this one, the agenda of these presentations coming from country profiles, what is Unitalia Indonesia, what is Italian higher education systems, reasons why you study in Italy, scholarships, collaborates, and yes, special information for you, for the audience of these events, and contact informations. Next. Okay, let me introduce myself. My name is Romero, coming from Unitalia Indonesia, because we have actually not many countries having Unitalia itself, because we are coming from MIPA. MIPA, one of Italian languages, the abbreviations coming from the Ministry of Foreign Affairs in Italy. Okay, next. Okay, we continue why you choose Italy. Okay, next. Now, this one about statistic data, Italy as country profiles. So we have the oldest European university founded in Italy. We call it Università di Bologna. And also Italy, one of G8 countries in the world. And also Italy quite famous with a very well-known of tourism. So mostly yearly people coming to Italy, 65 millions to come to visit Italy itself. And next, we are talking about Unitalia. What is Unitalia and what we are? And okay, next slide, please. Yes. So a part of the Ministry of Foreign Affairs in Roma. So we have 5 branches. A part of Italy. We have in India. We have in China mainland. We have in Iran, we have in Vietnam, and the last one, Indonesia. So Indonesia established in 2012. So we experience like more than 1 decade already here in Indonesia, and mostly we are promoting Italian higher educations, and also we made some of activities to promote Italian higher educations among Indonesian higher educations and also some of the high schools in Indonesia. So from Sabang to Merauke, so we already 1 decade experience to promote Italian higher educations. Next. So these 3 pillars, what we are to do, actually we help students to prepare and also introducing Italian higher educations. And one of the informations, Italy is one of country destinations to study abroad, not only for Asia, also Latin America, and also some students coming from US continue their higher educations in Italy. Why? We can explain more in the reasons why you study in Italy. Next. Now we are talking about Italian higher education systems. It's quite different with Indonesia higher education systems. Next. Okay, we divide it into two specific here, university-based and AFAM-based. AFAM, one of the Italian abbreviations, focusing for university that focuses for music and art. So university mostly focus on research, applied science and science-based, and AFAM-based focusing on music and art. So we divide it into 2. Well, next. This is about the systems. So basically, basic educations, they accept for those students that's already finished 12 years educations, which means Indonesia, they have 12 years educations, but in Italy, basic educations, the durations will be 13 years. With the scheme 535, for Indonesia, the scheme 633. Okay, so that's the difference, basic education from Indonesia and Italy. Continue to laurea, the durations for laurea or very quite famous, we call it as bachelor degree. The durations will be 3 years in Italy. Laurea magistrale, master degree program, the durations will be 2 years. But again, we have specializing master here. The master degree, the durations only 1 year, but 1 year master degree only focusing on professional level. If you intend to continue to PhD level, then you should choose laurea magistrale. The durations will be in 2 years. Okay, the title also master, but again, specifically professional and education-based. Okay, continue to PhD level, we call it Dottorato di Ricerca. It was about vacancy. What is vacancy? So actually the university will pay the PhD candidate. In the other country, the PhD, like we invest into university, but in Italy, the university invests to the PhD candidates. So the PhD will be paid by university to do research. So it's quite unique here. The durations will be 3 until 4 years study programs. Okay, next. So this is the statistic data. We have 68 public university that have been recognized by Italian ministry and 19 private university. Maybe some of you didn't familiar what is the name of the university. For example, like Università di Roma, Siena, Padova, Salento, Siena, Firenze. That's the name of the city in Italy. Very easy to divide it which one public and which one private. For those followed by the name of the city, like for example, like La Sapienza Roma, Università di Padova, Siena, Pisa, it was public university. An example for the privates, you can see at the bottom, Università Commerciale Bocconi. It was one of the top Italian university, but it was private one that focusing on economic, business and management and finance. And also we have Politecnico. What is the difference between Università and Politecnico? University based, it was about the scientific, and then also for Politecnico, mostly they focus on research based. So like practical 60 to 70, and then the theoretical frameworks will be 30%. Okay, next. Talking about AFAM. What is AFAM? AFAM call that Italian institution that focusing for music and arts for those students that interested in music, drama, film, dance. They continue to AFAM University. So we have 132 AFAM institutions that have been recognized by Italian ministry. Next. Okay, we are talking about the reasons why you study in Italy. So we have 7 reasons here. Next, please. Okay, all of you can see the 7 reasons why you study in Italy. We have excellencies, we have professionality, labor market, flexibility, scholarships. I will explain scholarship later on, and also part-time job. The students can do part-time job 20 hours per week maximums, and also life quality. Why life quality? Because in Italy, if you walk like 10 meters, if you walk 20 meters, like it was Instagrammable, with the historical of the Europes, and also the city quite beautiful, actually. Next, talking about entrepreneurs. Okay, in Italy, mostly Italian higher educations already support about entrepreneurs because small medium enterprises and also local government fully support for those entrepreneurs because they have incubators and also accelerator inside the university to support students in every majors to do and also having entrepreneur skills in their personal development skills. Next, talking about, okay, we break down, one by one the reasons why you study in Italy. Talking about quality, innovations, and traditions, because like Italy, the history, like the video at the beginning, rooted in the past, we shape the futures. So for those, some of you, the history of, I'm not talking about Italy, I'm talking about European higher educations in Europe. For those familiar Bologna process, the history of Bologna process. So the system that implemented in Europe, education system coming from Bologna process. Bologna process means Bologna, one of the city in Italy, and also Bologna, one of the oldest European university. They saved the system in Europe. So the locations in Bologna. And also some of Italian university already recognized and accredited by QS World University. So it means it was good with high quality standard. And also one of the reasons why in Italy about super affordable tuition fee programs in every majors, especially for the Indonesian passport holder. Why? Because Indonesia part of third level. So the tuition fee starting 400 euro per year. It costs like 7 million rupiah per year. You can take medical school, you can take engineering, you can take science, you can take architecture. Only paid you like 400 euro. And then it can be decreased based on family income. Okay, next. Now about top level English courses. So entirely we have 700 almost taught in English programs. For example, management, science, engineering, architecture, design, and medicine. Medicine, it was medical school. In Europe, medicine and surgery, we call it as medical school in Europe. So all information you can take to our portal, www.universitali.it. It was the portal coming from Italian ministry. Okay, next. Talking about tuition fee, yes, I already informed before, super affordables, and also we have scholarship, but mostly the rate of tuition fee in Italy, it costs you 400 until 1,000 euro per year. Next, talk about opportunity again. After graduates, you can stay 1 year extend to look for any job, not only in Italy, but also in Europe member state. Okay, next. Okay, now we inform about the scholarship opportunity. Please kindly attention because this quite very important for you. Next slide, please. Okay, so we propose here 4 types of scholarships coming from scholarship, merit-based scholarship from university. The second one about regional scholarships. The third one, MIPA scholarship. MIPA actually abbreviations coming from the Minister of Foreign Affairs. So MOFA in Italy offered scholarship for international students. And the last one, Invest Your Talents. So I will explain one by one. Next, merit-based scholarships. So every university in Italy, they offered merit-based scholarships to international students, not only international, but local students also. So every university has their name, uniqueness of scholarship itself. For example, like silver, gold, platinum coming from Polimi, Polytechnic di Milano, to Polito coming from Polito, and also Unibo, they have Article 1 and Article 2 for the scholarship itself. Next slide. The scholarship about DSU. DSU stands for Diritto allo Studio Universitario, or very famous, we call it as regional scholarship in Italy. So every province in Italy has their budget to support international students to give financial support during their study in Italy. For example, Lombardy, like Milan, Veneto regions like Padova, Venezia, they have their also the budgets. Next. The third one coming from MIPA, Italian Minister of Foreign Affairs. MIPA offered you this scholarship. It was fully funded scholarships. So this is the very general requirements. They support for masters and PhD candidates also. And also they offered intensive Italian course directly in Italy. Next, the last one, a very super prestigious scholarship offered by Italian Ministry, we call it Invest Your Talent. Why Invest Your Talent? Because they're focusing in these 5 major programs. For example, engineering, advanced technology, architecture, design, economic, and management. And what is the benefit of Invest Your Talent? Next, this one, the benefit of Invest Your Talent. You can get intensive Italian language for free, and also tuition fee waiver, scholarships, student support, and then the opportunity to get internship in Italian brand company. We know Italian brand company very prestigious and very luxury. Okay, so one of the prestigious scholarship offered by Italian Ministry. Next one, talking about Indonesians government to give scholarship to study in Italy. We have LPDP and we have ISMA. So I will explain one by one. Next, LPDP. So we have 9 Italian university already incorporated with LPDP. 5 of them funded all subjects coming from bachelor until PhD level. We have Bologna, Padova, La Sapienza Roma, Polimi, Politecnico di Milano, and also Università degli Studi di Milano. UNIMI, University of Milan. So those 5, all of them are public university. And next one, the other 4, based on subject, we have Bocconi, we have Polito for engineering petroleum, we have Trento here for the remote sensing, ground-based. So Trento has their programs and already incorporated with LPDP. And the last one, Scuola Normale Superiore, only for PhD candidate, specific in classic and ancient history. Next, about ISMA. Yeah, we know ISMA is one of prestigious for undergraduate students to do exchange 1 semester in Italy. We have 3 Italian university. We have La Sapienza, we have Unipi, Università di Pisa, and then the last one, Università degli Studi di Padova, or University of Padua. So those 3 institutions, they accept 100 Indonesian students to do exchange in their university. Next. Okay, collaborate with us. The next agenda. Next, please. Okay. Actually, in Italia, open to do collaborations with Indonesian higher educations. And next, this one timeline, that the new timeline that we have already dealt. So last month we cooperated with Global Catalyst to do study visit in Milan. So high school student visit to Italy, and also we cooperate with Sekolahmu. We incorporate also one of the high school in Central Java, Semarang. And also we have MOU Italian cultures with Trisakti, and the last one, okay, international conference from Binus. So this one, our newest collaborations, and currently this year's Unitalia cooperate with some of public and private Indonesian university to do MOU and MOA. Next. Scholarship project. Before please, the previous one. Okay, scholarship projects. So Unitalia already cooperate with Festival Indonesia and also ISMA, LPDP, and for those students having interest for internship with Unitalia. So starting September last year, we opened internship program. Next. Special for you. This is general information for you to study in Italy. Next one, please. For high school graduates, this is general for teachers here, high school teachers here, vocational high school teachers here. This information can be important for you. So for the high school graduate, just prepare these documents. And the next, for bachelor graduates, prepare these documents to continue study in Italy. And also for master graduate to do PhD level. Next, just prepare these documents. The most important for master graduates is recommendation letter and also research proposal, maximum 3 pages. We only need 3 pages. We don't need like 10 pages, 5 pages, no. Just 3 pages maximum. Next one. Okay. That's all. I open with any questions in after. So this is the contact information that can be useful for you. We have social media account, and also we have WhatsApp and email address. So thank you. Next one, please. Thank you very much. Grazie a tutti. Thank you very much. You're welcome. Now back to MC.
Okay, thank you, Mr. Romero Sinaga, for this great presentation. The next agenda is scientific seminar with the theme Data Reduction and Machine Learning Applied to Geophysical Time Series. The seminar will be delivered by scientific attaché at the Italian Embassy, Mr. Roberto Carniel. To Mr. Roberto Carniel, please come to the stage.
And to the laser. Green one. I go far away. Maybe you should decrease the volume. Maybe. Yeah. Can you put the presentation? Yeah. But it's still very high, the volume, I think. It's resonance. Yeah. Maybe we should decrease the volume. I don't know if here or there. I don't know. Okay. So I'm Roberto Carniel. So I'm the scientific attaché in the embassy of Italy in Jakarta. I just started 1st December 2022. After many years, as the ambassador was saying before, we had scientific attaché before, but for many years there was a gap, so there was nobody there. So I'm happy to have started this job, this opportunity, and my main task is to promote the scientific and research collaboration between the two countries, Italy and Indonesia. So let's say that I kind of complementary to Romero, because Romero is promoting the collaboration and interchange of students. So at the undergraduate up to the PhD level, I started the PhD level and above. Okay. So also for for professor and researcher, that is the researcher. So we will be talking about data reduction and machine learning applied to geophysical time series. So basically we are talking about time series analysis. So what is a signal? A signal is simply a function, I mean a parameter that depends on another parameter. For example, temperature is a function of time, pressure is a function of time, I don't know, seismic velocity, the velocity of the ground is a function of time. But also, for example, pressure is a function of temperature and volume. Okay, so anything that depends on anything else. But if we have a single independent variable, and this single independent variable, which was, you know, in 2 or 3 of my examples, okay, is time, okay, then we can talk about time series. Okay. So a time series is naturally continuous because time is continuous, but usually for, let's say, for logistical and practical purposes, we are forced to discretize. So our time will be discretized, like every second, every minute, 100 times per second, or something like that. So in this case, we talk about discrete signal. So where do these time series come from? They come from sensors usually. So we measure something experimentally, although of course they can come also from modeling, but usually it is experimental time series, and we can assume that these things that we are measuring are observable of a dynamical system, a physical system that generates this. For example, a volcano. Okay, so a volcano is a physical dynamical system that generates a dynamics and internal dynamics and produces some outputs, some observables that you can measure: the seismic velocity, the amount of gas, etc., the temperature. But in general, we are not able to know all the details of what is going on inside the volcano. So we don't know how it works, this dynamical system. We just assume that there is a dynamical system, a deterministic dynamical system. So our main task, when we have a lot of data, we can put, you know, hundreds of seismometers and sensors, etc. We have a huge amount of data. But we have to reduce this data because we have too much, too many data. So we have to reduce it, but still to keep the most of information. So we want few data, but very informative. That's the process of data reduction. So, for example, in this case, this was, okay. So, for example, here, okay, we have this distribution of points, okay, F2 and F1 are the two coordinates, okay, the original coordinates, and we say, okay, we want to compress the data. We only want one number, only, you have to choose F1 or F2, okay. And in this case, it's very difficult because if we choose F1 or if you choose F2, and we throw away the other ones, we lose half of the information, basically. But if we change just the coordinate system and we use E1 and E2, then it's very easy to choose. Okay, we keep E1 and we throw away E2 because E1 has the maximum variance. Okay, so this is a short example, simple example of data reduction. Okay, so just changing the coordinate system. Of course, we can have, you know, more sophisticated techniques. So, what is one of the time series I'm more interested to study is volcanic tremor. What is volcanic tremor? Someone call it seismic noise. Okay, I don't like to call it seismic noise because noise for me is something that we don't want to see. We are not interested. Signals is what we want to see. Noise is what we don't want to see. Okay, so it's a contamination. So we have volcanic tremor every time. It's a continuous tremor, a continuous signal, which happens every time a fluid is moving on a volcano, okay, or inside a volcano. So this fluid can be magma, can be water, can be gas, even can be ice. Ice moving produces tremor. It is called ice tremor, okay? Even without a volcano, actually. Yeah. So in the glaciers. So the question is, can a fluid move within a volcano without producing a seismic signal? And my answer is simple. No, it cannot. Why? Because when it moves, it touches the borders, okay? And it interacts, it transmits kinetic energy, and this kinetic energy is actually seismic waves that travel around the volcano, okay? So, if The answer is no. Okay, so if we go close enough, this is an ornito in Dalol in Ethiopia. Okay, so here we have just single drops of water that come up and erupt, okay, and deposit salt, and then they are building these ornitos. Okay, so if we go close enough, we put a microphone, an infrasonic sensor, a seismometer, we record tremor. But the fluid is very, very little. The key point is we have to go close enough. Okay, so if we see or we don't see tremor, it does not depend on the volcano. It depends on us. Depends on our capacity to build a monitoring system that is able to see, to record that volcano, that tremor. Okay. I already told about the difference between seismic noise, but within the seismic noise, we can have volcanic tremor. So volcanic tremor can be hidden in this noise. Maybe we have, we talk about signal to noise ratio. Sometimes in the good case, signal is maybe 90 times the energy of the noise, but sometimes it's the opposite. We have a very tiny volcanic tremor hidden in 90% of noise. Okay. So we have, okay, this is actually a paper that I always cite, actually a comment to a paper, because there was a paper on Ambrin volcano in Vanuatu where they were counting, okay, this number of volcanic tremors with duration, blah, 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 have been detected. And my point is exactly that they are not tremor episodes. They are periods of time where you are able to see the tremor or recognize the tremor. Okay, but the tremor is always there. Okay, so it is also possible to try to take out this maybe tiny amount of tremor from the seismic noise, or simply if we have 90% tremor and 10% noise, just to throw away this 10% of noise. This can be done with several techniques that are able to separate independent sources, because the key point is that. So we have independent sources that could be also volcanic. We can have, for example, two craters that are producing tremor. At the same time, we want to separate one from the other. This is also another example. So in this case, there are techniques like singular value decomposition, independent component analysis, non-negative matrix factorization. There is a number of techniques. Of course, during this talk, the audience is heterogeneous, so I will not go into the detail. I want to transmit the concepts, okay, the ideas. So another thing that sometimes we look at a signal and we say, is this tremor or not? Is there tremor here or not? We look at the seismogram and we say, I don't know. Okay. So one way of looking at the tremor and decide if at a signal and decide if there is tremor or not is to see the interaction with external triggers. The best example is earthquakes. Okay. So we have an earthquake close to the volcano. We look at the tremor of this signal and we ask ourselves, does it change before and after the earthquake? If it changes, it means that there is something, okay, volcanic, that is influenced by the earthquake. If there is nothing, of course, if you recognize that it's coming from an industry, for example, of course, this is not influenced by the occurrence of the earthquake. Maybe in the exact instant, then there is the people running away, but but afterwards the tremor remains the same. Okay, so that's one side. Okay, so the earthquakes can influence the characteristic of tremor. On the other side, actually, we can also, if they are produced by the same process, so in this case we are talking about volcano-tectonic events, we can use the tremor, the characteristic of the tremor, to forecast the next tectonic event, or volcano-tectonic event. Okay, this we applied, for example, in Tenerife. Okay, but this is kind of a special case. Okay, so how can we do that? So how can we look at the time evolution of tremor? If we look at the tremor, just like this, we don't see the change, okay? But we have to find special parameters, the right parameters that show us this change, okay? There are many, okay? Some are very simple, some are more complicated or esoteric, as one friend of mine or colleague of mine, say. There is a paper that I wrote, a review paper. I was asked to write in Bulletin of Volcanology in 2014, where it summarizes all these ideas. So basically, we have different types of time series that can be in a database, on the web, or wherever you want. Okay, then we can extract several parameters with several methods from this time series and basically look at the same signals with different eyes, with different ways. There is a phrase of Heisenberg that said that it's not the nature that we observe, but the nature under our methods of observation. Okay, the best example, or a simple example, is the stars. Okay, we were looking at the stars for many years, just looking at the telescope. Okay, with Galileo. Okay, since Galileo, but then, in a certain point, we decided to measure X-rays, okay? And we started to see things that we never saw before, because it's completely different way of looking at the same thing. So here, for example, we have a seismic record of Villarrica just one day in Chile, okay? So it starts from here, it goes down there, every line is half an hour, okay? So what we can, if we want to describe this, of course, we have these events, but most of it is tremor, okay? Is it tremor, is it noise? Well, we can decide later, but what if I have to describe this, the simplest way to describe this is say, okay, going from the beginning to the end, it becomes bigger, okay? Now, how can we quantify how big it is? Okay, we need a parameter to say how big it is. This looks very simple, okay, question, but still we have a lot of variability. We have a lot of freedom to define. We have R-sum, which is based on the modulus of the signal. We have R-sum that is based on the energy, so it's the square. Then we can say, no, I'm not interested in that frequency band, I want to throw it away. So we filter and then we apply the same thing, okay? And then there is the big question, how long should, so it's big, I compute this bigness every second, every minute, every 10 minutes, every hour, okay? And the results can be completely different. So, for example, here, this is an example from Mount St. Helens, in not the big one, in 2004, okay? So this is the same parameter, okay? But this is computed every 10 minutes, and this is computed every minute, okay? And you can see the picture is completely different, okay? So even this simple choice of choosing, you know, the integration time can affect a lot what you see or you don't see. And then we can ask ourselves, is this parameter, so we put a seismic station, we measure the time evolution of the amplitude of the tremor. Okay, and then we ask, first of all, the first thing to understand if a parameter is good or not, makes sense or not, because I can invent any parameter. If I plot the time evolution, okay, I must see something coherent. If I see a parameter, for example, like this, that jumps completely, you know, up and down, this is not a useful parameter. Okay, because it does not, I cannot see trends, I cannot see anything there, okay? But this is a good parameter because it has trends, it follows, it goes regularly, and then I ask myself, is it related to the source or to my specific station? Okay, I put another station somewhere else and I do the same. If the two go the same pattern, okay, I can say, well, this is come from the source, evidently, okay, it's not a passive effect, it's not a side effect, etc. Okay. And this is good sign. Of course, we can use also the ratio between these amplitudes to determine, for example, a simple distance from the source, if we assume that everything is homogeneous, blah, 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 okay. But we can actually do this, for example, for different periods. In this case, we use tremor, okay? This is Erta in Ethiopia, okay? This is a lava lake, and we recorded with 3 seismic stations. We used the amplitude of the 3 seismic stations, we did the ratio, and we computed, you know, the location, okay? Of course, the model that we use is a very bad one. So just everything is uniform, same velocity, same density, okay. So the model is bullshit, okay? But I don't believe, so for this reason, I don't believe that these are the location, these are 10 minutes each, for example, or 1 minute, I don't remember, 1 minute each, I think, okay. I don't believe that these are the real location of tremor. But I do believe that the tremor comes more or less always from the same place. When I see another period and I see this, I don't believe in the location, but I believe that these locations are different from this. So something has changed, okay? And this is actually, then it was linked to the presence of two regimes of the lava lake. One was very fast convection and the other one was slow convection, okay? So this is a good example because it shows that even if our parameter is not perfect, we are not interested in the absolute value of the parameter. We are interested in looking for changes, okay? So we don't care about the precision of the parameter. But if we see a sharp change, then we believe in the change. Not in the absolute value here, not in the absolute value here, but in the change we believe, okay? So amplitude can be used for forecast. Amplitude is a very simple parameter, but if we see the time evolution and we see an acceleration, something like that, okay, we can say that some, for example, this is a displacement, for example, okay, we see, we were talking yesterday about moving, one part of the Merapi with respect to the other. It is constantly moving, but if suddenly this starts to accelerate, that's not a good sign, okay? And we can use this acceleration, actually the inverse of it, to determine the time of failure. And this is the failure forecast method, but it's just based on amplitude, okay? Again, we wrote a review paper in, 2008, very old, okay? But since that moment, other paper came out, and they continue to work on different variations of this seismic, but the basic idea is still the amplitude or the number of events, for example, but for example, special kind of event. So you can use tremor, you can use seismic event, you can use the energy of seismic event, you can use the energy of tremor, etc. Then the other interaction that I was saying, okay, the thing that the earthquake can influence the tremor. Now, spectrogram. Spectrogram is a tool that everybody uses in seismology, but not only in seismology, in electrical engineering, okay. And spectrogram is the best example of a parameter or a method that is theoretically absolutely well defined, okay? Why? Because the spectrogram is simply like this. We have a time series. We divide it in window, okay, 1, 2, 3, 4, for example, 1 minute or 10 minutes, whatever, okay. We compute the spectrum of this, which is the distribution of energy for each frequency, or amplitude, okay. We compute the spectrum here, but to compute this spectrum, we are assuming, because the method of spectral analysis says that the signal is stationary. Okay, stationary means that it does not change with time, okay? Then we take another window, we compute another spectrum, and then we put some fancy colors, we put this here, and we say, we study how this frequency contact changes with time, okay? But we compute the spectrum under the hypothesis that the signal does not change in time. Okay, so conceptually, the spectrogram is complete nonsense, okay? Everybody uses it, and it works. So we don't need to have a perfect theory for a parameter to work, okay? And this is one of the best examples, okay? But again, to compute the spectrogram, okay, I said, okay, I take the window. How long is the window? We already seen. If I take 10 seconds or 1 minute or 10 minutes, the results are completely different. Also because the longer the time series, the best the frequency resolution I get. But if I get a long window, then I lose the time variations. Okay, so it's a kind of how do you say, la coperta è troppo corta in Italian, no? So something that you try to cover, but it is too short. So if you put it, you cover your head, but then your feet remains out, etc. Okay, so we cannot have both. So we have to find a compromise, and then we can say, okay, we overlap the windows. So we have another choice. How much? What's percentage? 50%, 20%, 10%? Which frequency range should I look at? From 0 to 10, from 0 to 100, okay? Then what kind of windowing to avoid problems? What kind of normalization do I apply? So it is the idea of the spectrogram can be then modified, and you have hundreds of different methods, basically. Sometimes you can see clearly something, and sometimes you don't see anything with the same method, okay? You can show the spectrogram like this. You can show the spectrogram like this. You can show the spectrogram like this. You can show the spectrogram like this, okay? And here is a wonderful example where you see the importance of normalization. This is the same data, the same spectrogram. The only thing that changes is the color scale. Okay, so here we normalize the spectrum from 2006 to 2018. Okay, so we use the same color for all and of course, the red appears only here, okay, where there was a lot of activity. But if we decide to forget about the amplitude variation, which we can look at with other methods like RSUM, okay, and we say, I don't care about the amplitude variation, I only care about the frequency distribution in the single window, so I normalize a single window. What you get is this. This is the same data, same method, just the normalization. So you divide by the sum of this. And you see that you see completely different things. You lose something because you don't see that this period is much more energetic than everything else. But you see a lot of changes that here you don't see. Okay? Then from the spectrum, in each window you have, I mean, if you had 1,000 data, you get 1,000 data in the spectrum. Okay, it's too much, too many. We want to do data reduction. So what is the essential thing here? Okay, for me it's important the fact that the red is here, okay, and this red moves like this and goes up, for example, okay. This is the important thing for me, okay. So I should look for the dominant frequency, for example. So I can extract, for example, the average frequency, the mean frequency, the dominant frequency, the standard deviation of the spectrum. Is it very narrow, only one frequency, or it is spread away? Okay. And then I can, for example, this maximum and mean frequency looks almost the same, but for example here, okay, we have two peaks. The maximum frequency is this one, where we have the highest peak. But here, the mean frequency is almost in the middle between the two peaks. Of course, a little closer to this because it is higher. But if we go here, okay, we move this peak a little higher, then this jumps from one to the other, but this just moves a little bit. So they are giving us, again, complementary information. So it's not that one is better than the other. They are showing different things. Sometimes one sees a change and the other does not, or vice versa. Okay, this is, for example, the evolution in Ambrim, again, for 3 months maybe, okay, of the two parameters. And you see that, for example, this stable part here, you don't see too, it's not very notable here. Okay, so they are showing different things. And then you can elaborate on this. For example, okay, I don't take one peak, I take the first 5 peaks, the first 10 peaks, etc. Okay, and you can combine, you can combine actually with the RSUM, because here we decided not to use, so to normalize, we want to lose the amplitude information. Okay. But here we have it, okay, so we can combine the two, and then we can, for example, identify that this was magma injection, then there was the domain placement, etc. Okay. Of course, it's not so straightforward, it does not come out automatically, you have to think about the data later, okay. Then, but there are, let's say, many ways of presenting dominant frequency, etc. For example, one like this also, where you just take 1 minute every day, for example, and you see if the relevant peak changes or not. For example, here you see the appearance of a new peak that was not there before, etc. Okay, you can develop software to automatically find peaks which are difficult to see in the original plot. And for example, here you can notice that these peaks are regularly spaced in frequency. So you think maybe there is a resonance there. And the resonance is important because sometimes you get a resonance and this resonance changes with time. And when it does this, this is called gliding lines. This is not a good sign because there is something accelerating. It's like the case before. And in this case, this is Montserrat. You had this acceleration and then suddenly you had the dome collapse. Okay? This is another case in Redoubt. Another key point is if we have more instruments, it is not a good idea that, the seismologists look at the seismic data, the deformation, look at the deformation data, the thermal, look at the thermal data. We have to put together the data, okay? So on the top, we have the spectrogram for seismic data, and on the bottom, we have the data from, this is Erta in Ethiopia, the lava lake regimes that we were talking about before, okay? And here we see that we can see the same changes in the same time in the seismic data, in the thermal data, okay? And this is actually the regime, so there is a high velocity, high convective regimes, and then there is a low convective regimes. And we can see it in the thermal data and in the seismic data. But there, if we do a data reduction and we compare temperature with the average frequency, okay, of the seismic data, we get again these changes very clearly. But sometimes they do not agree. For example, here you see that does not agree with this. And this is why they are looking at different things, because the thermal data was looking at something like 2 meters by 2 meters in the lava lake, but the seismic data is seeing everything, what is going on. Okay. Okay, going back to our idea of the fact that our time series come from the, how do you say, the dynamical system, okay? Tell me when I have 10 minutes left. We can say that, okay, we have a time series, but can we reconstruct the dynamics from this single time series? Okay, one thing, no, it's impossible. But the idea of Takens in the 80s was this. For example, things about the climate, okay? We have temperature, pressure, and humidity, okay? We don't have pressure and humidity, we only have temperature. But the temperature today depends on the pressure of yesterday and on the humidity of yesterday and in the previous days. So within that temperature measurement, there is information about the pressure and the humidity in the previous days, okay? And that's the key point, okay? So I can try to start with a single time series and then use this idea of deterministic time series, the dynamical system, to take the same time series, delayed in time. Actually, graphically should go the other way, but it looks nicer this way. Okay, so I choose a tau. For example, I delayed by 1 day or by 1 minute or 1 hour. Okay, and then I use these coordinates as 3 different independent coordinates to choose and draw the trajectory of this. And this can be, it was demonstrated by Takens that this is, basically there is a bijection between this and the original trajectory in the dynamical space. Okay, under simple hypotheses. First, that there is no noise. Second, that the time series is of infinite length. The mathematicians are like this, they put simple hypotheses, which of course we never can apply. Okay, and then there are parameters that are used to use this method, which are embedding dimension, which is the number of coordinates that I use, and the delay time, how much I shift this. And this can also be determined with, I don't enter into the details of this, but then I can look at these parameters and the evolution with time, okay? And this is another very good example that shows that across many years, okay, this evolution is coherent, so I did not invent an absurd parameter. I invented something that is coherent with time, okay? And then it's difficult to see, but there is another plot below, which is light gray, okay, which is computed with completely different method, okay, to estimate the same quantity, and they go together, okay? So which means that the parameter is really significant and it belongs to the source, okay? And then you can compare it with another way of looking at the tau is the first zero of the autocorrelation function. You take the autocorrelation of the signal and you look for the first zero. Okay, here it's not very visible, but you can see that here you have the first zero of the autocorrelation function at the volcano. There is an earthquake, and it jumps. Okay, so you can see here immediately that there is tremor there. Okay, because there was a strong debate at that time if there was tremor or not. And there, okay, and you can see that these parameters can be also computed in different stations and see if they go together. You can see changes here. Here especially, and here it's very interesting that you see this divergence of these parameters. Okay, so they go together until here, and then they diverge. It means that there is something going on close to the blue station, which is too small for the black station to take. So probably there is another source Bohr close to the blue station. Okay, and this is of course very important. Then you can use the concept of correlation to correlate with other things, for example, with the lunar cycles, to see if the moon is influencing your in this case it was an hydrothermal system in Vakari in New Zealand. This is a nice paper because you see from the number of authors, okay, that you know, everybody was applying a different method, and we put everything together. This is a very good thing to do. But in Merap it was done. Yeah, in 2010. And so you can, for example, this is the seismic noise interferometry. That is also a way to look if between two stations there is a change in the path between the two. Okay, so if something is coming up in the middle, then you can see with this method. Okay, but finally, it's always time series analysis. Okay. Another way of looking at two signals is mutual information. So how much information is shared between the two? And then again, you can plot this, which is completely different. And conceptually is similar, but in practice, the method mathematically is completely different from the other one. But still, you see that in the same point, you have the divergence of the two. So another proof that in that moment, there is a new source appearing, independent from the other. Okay. Single variable composition, again, is a way of separating things within the signal. So we can basically, based on the entropy of each signal, okay, separate this and try looking for independence. So it's basically the concept at the base of this. So basically, we are rotating our coordinate system so that we use this as the first coordinate, and then we throw away this and we look for the second most important, and so on, so on, so on. Okay, and then we can see how this changes with time. This is an example at Popocatépetl in Mexico. Okay, and again we see that there is an earthquake 6.1. Okay, and we can see that this component, which is actually the third and fourth component by importance, okay, they are not affected by the earthquake. They continue. They don't care. But this component, the 1 and 2, the two most important, are very strongly affected by the earthquake, and they change. So it means that within the tremor, there are two parts. One part is probably volcanic, and is affected by the earthquake. The other part is not volcanic, and is not affected by the earthquake. But this is a nice case, because the one influence is the most important. But on Stromboli, we did the same, okay? Well, we look at dominant frequencies and other parameters, but this is interesting, okay? We see these clear changes, okay? The earthquake appears, and we have a clear changes in what? Sigma 3 and sigma 4. If we look at sigma 1 and sigma 2, we don't see anything. which means that the signal-to-noise ratio is so bad that the most important part is not volcanic, it's noise, okay? And this is, and sometimes you see cases where, I don't know, sigma 7 changes, okay? So very tiny component, yeah? But still, you are able to tell that this is significant. And actually, one can say, okay, I can see a change here, but you look at this because there is the earthquake there. For example, here there is a change, okay? Why don't you consider this, which is not related to the earthquake, okay? That's a good question, okay? So we applied a method, actually we adapted a method that was coming from econometrics, okay? So this is another message, okay? Don't look only at the paper in your field. Look what they are doing in other fields, and you copy the ideas, okay? This is actually, now is in machine learning, it is called transfer learning, okay? So we used this method, and we demonstrated basically that these points were exactly the points where the changes are the most significant during that period, okay? So the earthquake were associated to the most significant changes in the time series, okay? Then you can actually invent a parameter and ask yourself, can be used for forecasting, okay? So for example, I look at the temperature, okay? Can I use the temperature of today, yesterday, 2 days ago, to forecast the temperature of tomorrow, okay? In Jakarta it's very easy because more or less it's always the same, okay? But in Friuli, for example, in Udine, no, it's not like this, okay? So the question is, can we use that parameters to forecast the future, okay? Then the way of measuring this potential is by looking at the memory of this parameter. So if the parameter today remembers somehow the values of the past, then it's a good parameter. But a parameter that jumps up and down and does not remember what is happening in the previous days cannot be used to forecast the future, because if the present is not influenced by the past, of course, the future is not influenced by the present, okay? So you can quantify this with a tool called variogram, and actually you are looking for something that goes like this, okay? When you see something that goes like this, it means that the memory of the system is here, it is 30 hours. So it means that with these parameters, you are able to forecast, theoretically, up to 30 hours. So if you want to use these parameters to forecast 1 week in advance, it's nonsense, because the memory is too short, okay? So there are parameters that record a long memory, and there are parameters that just lose the memory very rapidly, okay? And this is also another good example, because this is the same variogram, but this is computed 8 days before a seismic event, and this is a parameter, the same parameter computed after, 8 days after the seismic event, okay? So the change is that here, basically, you only see the 24-hour cycles, which is anthropic, or could be meteorological also. And here you see the structure, which is the good one. It means that here, the tremor is very tiny. It does not appear. Here, the tremor is very strong, which means that the earthquake triggered the start of a tremor, or the start of a more energetic tremor. But we can do the opposite. We have cases where we have a clear tremor here, then there is the earthquake, and afterwards the tremor disappears. Okay, so the earthquakes are able to switch on and off, basically, the tremor, or energetic, less energetic, okay, because the tremor, remember, is always there, okay. Then, how can we use all this with machine learning? All these parameters that we can invent, okay, based on amplitude, spectral content, dynamic assistance, autocorrelation, moving average, or whatever, okay, they are all numbers. All these numbers can be put in a vector, okay. For example, in 1 minute, we compute 100 of different parameters. We have 100 numbers that characterize each minute, okay? And then we use machine learning to find out if there are minutes that are similar to each other and minus that are different from each other. So looking for regimes or changes. Again, we can use this machine learning with different methods. For example, artificial neural network, which is the classical one, which is based on actually our way of reasoning with the neurons. We can use two types of training because we need training. We can use supervised training, which is based on examples, like at school, okay, the maestra, the teacher, okay, teaches you, okay, this is an A, this is an A, this is an A, this is an A, okay, but they are always different. Every time you write, it's slightly different, okay. You give many examples, then this is a B, this is a B, this is a B, okay, and then you teach the machine to recognize. The same thing you can do, this is a VT, this is a VT volcano tectonic, this is volcano tectonic, but this is a rockfall, this is a rockfall, this is a rockfall, okay, same concept, okay. So you give a lot of examples and you train with the examples. What is the problem? That in many times, the A or B, everybody knows, if this is a volcano tectonic really, or it is a rockfall, maybe you say it's a rockfall and he says it's a volcano tectonic, okay, and we have a problem. So if the teacher is not good, the supervised method does not work, okay. So we can use the unsupervised training. The unsupervised training, you just give the data, and the machine learning learns which parts are similar to the other, okay. This is an example, self-organizing maps is an example of unsupervised, okay, that we used a lot on tremor. For example, we can have a simulated tremor with very different characteristics here. We have a part here, and a part here, and a part here. And we have to choose parameters to describe this. Of course, we could use the amplitude, because this is bigger, bigger, and bigger, but probably it's more efficient to use the frequency content, okay? So we can, instead of classifying this, we classify the spectrogram, okay? And then we get this auto self-organization of the map, and finally we use a clustering, and finally we get 3 colors on the map, 1, 2, 3, and then we see the characteristics of each spectrum, of each, and we can see how it evolves with time, okay? So we take every minute and we give it a color, green, blue, or red, okay? And here it is very nice because it is quite coherent. Again, if we do this, and then we plot the evolution in time, and we see a complete, mess, blue, green, red, blue, green, red, blue, 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 green, okay, it changes continuously, it means that the training was not very efficient, okay? But if we see something like this, very coherent for a while, and then suddenly it changes, there is this red part here, and then it goes into blue, okay? Then, of course, here you see that it's not perfectly coherent, but it is mostly blue, and this is a phreatic explosion, okay? It was a small phreatic explosion. This is Ruapeu volcano, New Zealand, okay? And here, we trained the data with this part here. We trained the machine with this part of the data. This was a small phreatic explosion in 2006, okay? And then we applied the same model to a big phreatic explosion in 2007, okay? And what we get is this. So you see that, of course, it is not perfect like the one before, but still we see that here we have a dominant green, okay, that suddenly merges into blue, okay, with some red here, and then we have the explosion, okay? So we have a similar behavior. Of course, it not always works so easily here, so yeah, but still, okay, so we can use, another thing that we can use these concepts is to, for example, how long does this blue part or this red part last? So how time before can we say, okay, there will be an explosion? Unfortunately, these two explosions were at Ruapeu, and there was, I think, someone there, but nobody was killed. But something similar happened at Wakari, and I don't know, 3-4 years ago, and several tourists were killed. So if you had something like this and able to see, okay, you just make a call, and then the helicopter goes away because it was an island. Then classifying events is another way of using machine learning. So as I was saying before, what is a rockfall, what is a VTU, etc. Okay, when you are in this situation, it's very easy to, it's boring, but it's very easy to do, manual classification. You make a trigger, then the trigger says, okay, you have these 100 events, you have to classify them, okay. And then you say, okay, this is volcanotectonic, this is okay. But when you get in a situation like this, you are in a problem, okay? You have a problem. Because, of course, first, if you see something like this, you're correct. This is, getting bad, okay? Second, you don't have the time, the physical time to do the classification. Because there are so many that you cannot classify by hand, okay? So, the good thing of machine learning is that it is not perfect, like actually also the human is not perfect, but also the machine learning is not perfect, but it is coherent, okay? So, if we have a statistical distribution here, okay, which may be reasonable, wrong, a little bit wrong, etc., but then it changes completely. For example, the number of LP increases, the percentage, then, we can interpret this, okay? And it can be done completely automatically. One way of doing it is again, with supervised or unsupervised, okay, model. And one way of doing it is with hidden Markov models, okay. Hidden Markov models are good because they can be used continuously on the data, okay. So you don't need a trigger, okay. So you just give the continuous stream to the network, and the network classifies it. Okay, this part is tremor, this part is VT, this part is garbage, because there is some spike, but, okay. In fact, it's a good idea also to give many examples of garbage, because so you can, for example, jump on the seismic station. You can put, electrical spikes and things like that, so that the machine learns that these are things that you don't have to care about. Okay. And then, of course, you can apply it, and if you actually another advantage of HMM, hidden Markov models, is that it uses actually the time evolution. Because, for example, in a VT, the P wave always comes before the S waves. So if you see the S wave before the P wave, this is not a VT, okay? And this is something that other methods do not use, this time information. So they classify window by window, but they don't care about the history. Hidden Markov models do this. And then the big problem is, for example, here you have Merapi, you have many data about Merapi, but Ness volcano is called, what's the name? The one that erupted in 1700 something, the Ness volcano to Merapi, to the, yeah, okay. This volcano never erupted in the last 200 years, okay? So we don't have any data, okay? So we see something, how can we train a model? We don't have data. So we can build a universal model, okay? So if we assume that, for example, Merapi behaves similarly to that, we can use Merapi data to train and then apply this model to the other. But the best thing is to take not only Merapi data, but also other volcanoes that behave similarly to Merapi, okay, and similar to the one that we want to classify, okay. So we build a universal model which at the end, even if it is built by supervised methodology, is finally basically in practice it is unsupervised, because we take it, we don't need any training, we just give it and start to classify. Okay. And there are actually several tools that were developed during a European project, Vulkan EAS, that you can actually download. You have Python code that you can use, straight away to try to classify your events. This was done in Udine by Guillermo Cortés. He was coming from Granada, and he's now back in Granada. Okay. And he worked also with Philippe Lesage in Grenoble, so it was a combined project. So it is something that you can use. And actually, going back to, this is an example, but if you look on the web, on the, for example, in all the deposits of source, of code, you can find many things that you can apply, okay, for free. And most of them are based on Python. So Python, I think, is the way to go. Okay, Then going back finally to the separation of volcanic tremor and seismic noise, or to extraction of different parts of the volcanic tremor, okay, I have another example. Actually, this is just to demonstrate it, because we talked a lot about seismic, well, we talked about a bit of thermal data, but this is infrasound data, okay. So actually here, this is in Shimoedake in Hiroshima in Japan. So we have, of course, it's a collaboration. Well, I never cited all the authors, but you know, you can see them. It's always a collaboration with local people. Yeah? And we had a station where there was co-located a seismometer and an infrasound sensor. Okay. The problem was that the infrasound sensor was recording nice signals from the volcano, and also a lot of noise coming from the wind mainly. Okay. So the question was, can we separate the wind and the volcanic part? Okay. With a single recording. Okay. And this is the idea. So the idea is that actually there was a previous paper by Mie Chihara and others, okay, where they presented this method. So we have the seismic data, the infrasound data, and well, this was maybe the amplitude, I don't remember, okay, but the key point was to look at the correlation again between the two. Okay, so if there is something coming from the volcano, the time basically difference between the seismic data and the infrasound data is coherent. Okay, so we see the appearance of very clear patterns here, okay, of autocorrelation, not autocorrelation, cross correlation in this case, between the seismic data and the infrasound data. Now, we keep the seismic data fixed, we don't touch it. We only take the infrasound data, and we apply this method of non-negative matrix factorization, which is a blind separation. So we have one signal and we give it, okay? So it separates the two parts that are most let's say, independent between them, okay? And then I have part A and part B, okay? And then I take part A and part B and I apply Mie method, okay? So I show this autocorrelation, okay? In part A, I see this. So I see that these patterns are enhanced, you see, that are much more visible. For example, in this part, you see, they are much more visible here than in the original data, okay? But in part B, they basically disappear, okay? So it means that part B is more volcanic, part A is more volcanic than the original record. Part B is less volcanic than so it's mostly noise. So we only keep this, and we are basically have filtered out the wind, okay? This blind separation was actually applied to several volcanoes, and we also applied to Merapi volcano. That was in 2008. So, you know, and after only 14 years, I managed to see the volcano. Okay. Okay. In this case, we separated actually the contribution from the sea, the sea noise, which is also sea microsound, is also a very important contamination. Okay. So, in conclusion, the key point is always to try to extract few parameters, but these few parameters should be very informative, okay? Talking about machine learning, if I want to build a machine that distinguishes between this thing here, okay, and a mouse, okay? There are several features. This is called features, the parameters, they are called features used in machine learning, okay? There are several features that can describe this. The size, the shape, the color. But if this is black, and my mouse is black, the color is a feature that normally we use, you know, every day. But for this purpose, the color is a feature that's completely useless. So it is useless to add data that is not able to distinguish between. So we have to think about the task, what we want to do. We want to distinguish this from this. For example, rockfall and pyroclastic flow, okay? Maybe the duration is very important, so the duration should be put as a parameter. We have to distinguish LP from VT, okay? By chance, at MIRAPI, statistically, the duration is the same, okay? So we don't add the duration if we want to distinguish this from this, okay? So we wanted to extract few parameters, but very important, informative, and able to distinguish two classes, okay? And then we can use this reduced data stream, because we have few parameters, to do machine learning, but also to see the time evolution and see if there are changes in this stream. Okay, and then of course we can use to classify events. And then of course there is the question of, for example, the tools will say, okay, this is a tremor regime, and then there is another tremor regime. So there is a change, significant change here. But then the interpretation of this is up to you, of course. You have to add more information, visual observation, etc., etc. Okay, so it's not like, you know, the machine that you do like this and it does everything for you. Okay, you just go and keep the salary. No, it does not work like that. Okay, so you can use, for example, the results to help to build your because there are physical changes. You can use it to build your models, for example. Okay, and all these reduced parameters can be used in feature vectors that can be used for classification with machine learning. Okay, and I think I will stop here because, yeah, I don't go near there. Okay. Of course, if you have questions, not necessarily now, but you know, it's, yeah, and yeah, of course, if you have questions now, you are welcome. Yeah, but in general, I mean, it's I mean, he has my contact, so you can ask. We to give. You are authorized to give my contacts to everybody. Okay, and then especially, I mean, if you have ideas that you want to implement and you think there can be someone in Italy that can do this with me, then ask me and I will try to help you to establish new collaborations. Okay, thank you.
Thank you to Mr. Roberto. And now it's time to break. We kindly ask the distinguished guests, ladies and gentlemen, to see the student invitation creation located at the entrance of this room. After the break, we have a roundtable discussion with the theme is how to integrate research result into monitoring speaker. We would like to join to all of invitation to join the roundtable discussion if you interest with that topic. We really thank you so much for the coming, especially for the school principal who have come today. And this is our last event for the scientific seminar. Thank you so much. And we have a break around 15 minutes. So after 15 minutes, you can back to this place again. Thank you so much. See you.
the red chairs. So you have to come as close as you can.
Welcome again to all distinguished guests, ladies and gentlemen. Now is the roundtable discussion with the topic discussion, how to integrate research result into monitoring speaker. This discussion will be led by Honorable Moderator, Mr. Wiwit Suryanto. And to Mr. Wiwit, please take the discussion.
So, thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Terima kasih ini Bapak Ibu yang masih bertahan di ruang ini meskipun kedinginan. They said that it's cold inside the room, so they want to go out, looking for warm temperature. So I'm honored to be moderator as for this roundtable discussion. It is actually a continuation of what Roberto already presented. But now we maybe also want to think about how to integrate the research results into the monitoring system, because this is something really important. Yeah. For the information that starting last of 2022, so BMKG initiate a consortium for hazard mitigation, especially for earthquakes and tsunami. And one of the key question or challenge actually is how we integrate the knowledge about time series analysis into the monitoring systems. And you just give a very inspiring presentation. A lot of us enjoying your talk, although another maybe didn't know what happens about the figure and the equation. But yeah, today we will discuss more focus in application on how we can integrate into the monitoring system. Maybe you have experience or you want to share something, please. Time is yours.
Yes. Okay. Towards the end of my presentation, I was mentioning, for example, Vulcan Years, okay, which is a project, which was a project funded by the European Union, where the main person was Guillermo Cortés from Granada, and the idea was exactly that, to produce a series of tools that could be used in reality. And so that system, or at least, I mean, all the, let's say, the software is released as open source. So you can download it, you can use it, but you can also modify it and make it better. Okay. Of course, it is always better to, to modify it, and having an interaction with the author, the original author, so that it can be, your modifications can be integrated also for other people. But then, of course, it's always happens, and there are the so-called forks, where one takes the code and modifies, then, you have different versions. Okay. But different versions of this software are actually running, for example, in Colima Observatory, in Mexico, in Popocatépetl, and I think they are experimenting also in Ecuador and some other countries, mainly in Latin America. But Latin America, because we had more contacts there, not because it was not a choice. But that is effectively a possibility. There are other software that can be used. One that comes to my mind is, I think it is called the Red Pi. That is also for classification of events. That is, the author is Alicia, also complicated name, something like that. okay? But there are many more there. So one thing that I surely recommend is to look into GitHub and other source repository, because there is a lot of it. So if you think about something before starting to program, search the web, because on the web you find a lot of software that can be used, libraries, but also full packages. Another one is for the analysis of seismic noise and autocorrelation between the station, looking for path differences, is MS Noise, done by Corentin Padron, Lecoq, yeah, in Belgium and France, and which is also very, very good. So there are many software there. Yeah. One thing I wanted to show is also if we can start the other. It's just for, don't be scared, it's just 4 slides, I think, and it's not my slides. I don't know if there is someone that can. Say it in Indonesia.
Mohon dibantu slide dari Pak Roberto yang part 2.
Because before coming here, I asked people from INGV. INGV is the Istituto Nazionale di Geofisica e Vulcanologia. That is the national institute in Italy. So we have a single national institute that is, let's say, which has the yes, okay, this, okay. Istituto Nazionale di Geofisica e Vulcanologia, which is now the only monitoring agency for volcanoes. It is also the monitoring agency for earthquakes, but there are also others. But let's say it is the only national one. Now we have some regional ones. For example, in my region, we have another one. But of course, there is exchange of data, etc. But what I wanted to was what I asked Ciro Del Negro, okay, who is the first author here, was to provide some other examples of how they use actually machine learning, and especially to prove you somehow, because of course I'm kind of biased. Actually, I did not mention in the talk, I forgot. I mentioned 2 reviews, one of, let's say, methods of looking for changes and regimes in the tremor, another one for the failure forecast method. There is another one for variogram, and there is actually there are 2. Let's say that there is one already published in a book by Caroline Emmett a couple of years ago about the applications of machine learning to volcanology, and there, of course, there is, I'm still biased because I'm working mainly with volcanic tremor, but so most of the examples are from seismology. But there are also other applications, other examples of applications, so you can have idea about the formation and geochemical data and gases, etc., thermal data. And I submitted a revised version of that, so an expanded version of that with new example, etc. Because the field is so rapid, that a review paper written in 2021 is already old. Because in the meanwhile, I found like 100 new papers that apply machine learning in volcanoes. So, okay. Here, I wanted to show this because these come from INGV, which is a monitoring agency. They also do research, of course, but they are mainly a monitoring agency. So they actually use these methods. And so in particular, INGV is all over Italy, but let's say that the historical centers are Osservatorio Vesuviano in Naples, and now it is called Osservatorio Etneo in Catania. So one is monitoring mainly Vesuvio, and the other one is monitoring mainly Etna, but also the Aeolian Islands. Okay. So they actually apply machine learning techniques also for other things, not only for seismology. So, for example, here we have a way of applying machine learning to classes, sorry, to recognize lava flows and map lava flows from satellite images. This is also a very interesting thing to do. So to look for free satellite images. Free satellite images, there are many that can be used and can be integrated also, of course, with ground data. The good thing of machine learning is that you can mix things up. You can take this feature vector, can contain parts that come from satellite, parts that come from the ground, come from seismology, from thermal data, gas data. So in this case, they use machine learning to map lava flows. Then they also use satellite data to recognize, because a stromboli, you know, strombolian activity is an activity very explosive but very mild, you know, very nice eruption, explosions like 150 meters high or something like that. Okay. But sometimes, from time to time, also stromboli makes, you know, things, bigger things, okay, which can be dangerous for tourists and for people there. Okay. So they made a machine learning, a machine to recognize these from satellite. Okay. And then we have this for example, for characterize the volcanic cloud components into, you know, when Etna erupts, you have this cloud. You can, from the satellite, classify what is inside. And finally, this is also another, actually, well, this is an application made by them, but there is a full project which is cited in my review. I cannot recall the name. Which actually takes the images systematically, all the satellite images, and looks for hotspots. So places where maybe in very remote areas where nobody is aware that, you know, an eruption is starting. Okay, so this is also another application. So I think, no, there was another one. Okay, this is also an interesting idea. So sometimes you can build a model, okay, with your computer, but this model is very computationally intensive. So you need a lot of computing power to run the model, okay? So what is the idea here is that in this case was applied to lava flows, but it can be applied to anything, okay? So the idea is that you use the model to generate, let's say you have a series of input to the model, you have the output of the model, okay, which you compute with the model, so taking a long time to process, okay, to process and get the results. But then when you have a number of examples, you use these examples to train a machine learning, okay, machine, okay, that can learn the task of the model. But of course, when you train this machine, then this machine is applied very fast. So it gives you the result in seconds, okay, or maybe less. So this is also another application. So you build a very complicated model, you use it to generate a series of examples, and then you teach a machine to emulate the model, but much faster. Okay. Of course, the results can be approximate, yeah, but maybe in a crisis, it can be, you know, useful. I would like to, you know, to hear if they have example.
Okay, as mentioned by Pak Roberto, that actually concerning the software, it's available actually anywhere, and also this is like the application that have been implemented, some of them, yeah, especially by INGV. So I am sure that here we have staff from BPPTKG, to Naneng and Basulis, and also from Geology Department. I think they have also experience concerning the time series analysis, and especially what you presented in previous presentation, and also Mas Erlan is working with image sequence, so it's also time series, but image series analysis. So first of all, I would like to give time to Nanning first. Maybe you have a comment on this kind of topic.
Thank you, Pak Vivit and Roberto. We are very interesting with this topic, and it is good that it is trigger us to do more effort for Merapi. Yeah. But I have a question. It is about this case in Merapi in this crisis. Yeah. Merapi eruption since 2021, yeah, 2021, and we concern for the deformation data. We already discussed about it. That's on the west area of the summit, inflated until 15 meters, while for the other side, less than 1 centimeter, yeah, and it is not continue. But for the west area, the deformation continue until now. And my question is, do you have experience about tremor that can indicate it if the collapse will be occur? Because we predict for the deformation not symmetric, and we predict it will be indication of the sector collapse. Do you have experience for the tremor which can be indication of the sector collapse?
So the machine learning has to learn from something. So either you provide, say, examples where you, for example, you can have previous cases where you had collapses. Okay, so you can use some features computed on the tremor before to see what happens before, and then say, okay, later there was a collapse. Okay, and of course you need to give also other examples where you have tremor and you don't have. For example, you can take, I don't know, you choose the time. Could be 1 day, 2 days. Okay, there are several 2 days. Okay, without collapse, and other 2 days with a collapse. So you can use that to train a machine so that you can apply then in real time and see what is the probability. Of course, machine learning is not the only way, because there are other, for example, Bayesian belief network is also an approach that was proposed in volcanology first by Willy Aspinall. And the good thing is that it kind of weights all the evidences. So, for example, there was actually, he applied it to the case of Galeras. I don't know if you remember, there was a volcanological meeting, and they organized an excursion, and during the excursion there was an explosion and several people died. And afterwards they said that before this explosion, in the seismic data there were tornillos. And these tornillos are LP, so long period events that have the shape of a tornillo, which is a screw, like a screw like this. Okay, that starts like this with the same frequencies, but then decreasing, damping. Okay, and they said that okay, this was a clear evidence that there would be an explosion. So why did you carry people up there? Okay, and Willy Aspinall made a serious analysis with Bayesian belief network where he tried to, because one information was that there were these tornillos, and these tornillos sometimes happen before an explosion, but sometimes they happen also without an explosion. Okay. Second, there were other evidences that pieces of evidence that were telling us that nothing would happen. The deformation was quiet, the gas was quiet, the temperature of the fumarole was quiet. Okay, so all the other parameters were telling us that nothing will happen. Okay, so his point is to build this machine, Bayesian belief network. This is a statistical thing. It's not machine learning. Okay, but still it's very useful for me. That weights the different evidence. So the seismic data is telling us something is going to happen, but we have also other data, and this other data is telling us that nothing is going to happen. So you can wait, and then you can also give some kind of weight, some kind of, and this you can also use for people's opinion. Okay, so you can make kind of I don't remember the name. Well, let's say, okay, somehow evaluation of the, because you present a series of questions to scientists, and what would be your inference looking this, and this. Some questions have an answer, a clear answer, okay, so it's true or false. You can do, you can write true or false. Yeah? But sometimes there are open questions. So questions like yours where there is no real answer, okay? And what is evaluated is not only the answer that you give, but also the confidence that you put in the answer. So there are people that are very has a lot of self-esteem and say, okay, it will happen this. Okay, I'm 100% sure. And other people that have a very, this will happen, but I'm not sure. Maybe this will happen, but my experience says, maybe there is a 30% probability that this will happen. Yeah? My idea is this, but and all this can be weighted so that you can get a final evaluation of all the evidence and all the opinion of the people. And that, I think, is a very interesting. So you should look at the papers of Willy Aspinall. And he's analyzing also data for terrorism, for other kind of hazard, not only for volcanoes, but and he has very, very nice ideas. So there is no answer, but of course the answer is to look in the past. Yeah, of course. Yeah, but or to similar volcanoes that happen, that show similar things. Which is not easy. I admit it's not easy. Yeah. But yes, it is very, very, very strange. This strong asymmetric, and I don't know. The question is how sustainable it is. I mean, how long can it? Because you told me that it was not accelerated, but how long has this been? How long has this been going on? Like the song, it is 1 year or 2 years. That is okay. So So in 2 years it moved. How much?
15.
Yeah, because okay, it does not accelerate, but how far can it go? Yeah, that's and of course, especially why does it move? That's the main point. So it's I would be.
So the answer is no answer.
Yeah, of course I don't have an answer. But, but I can suggest ideas how to find an answer.
So, but
it's like you don't give fish to the hungry, but you teach them to fish.
the point is, machine learning need something as an example or reference, to be.
No, something similar. I'm not aware of, but maybe there is. Of course, you have to look into the literature and see.
Yeah. Okay. So Harus banyak membaca literatur. Okay, anything would like to asking or comment?
Yeah, it is become difficult for us to analyze Merapi activity because we have no reference for the deformation pattern like this. For example, at Sakurajima volcano, at the other volcano, almost deformation is symmetric, and it is can be analysis by theoretical of deformation analysis by elastic model, but it is not symmetric. 15 meter for the west area and the others area less than 1 meters, less than 1 centimeter. So it is 1,000 times compared with the others deformation, and we call this not symmetric. And we agree, all of the scientists last year, yeah, Pak Agung Harijoko and Pak Wiwit to discuss about it, and we agree it is will be indicator for the sector collapse. But the problem is when the sector collapse will be occurred. And I want to know reference or the other experience that show another not symmetric deformation, maybe at the other volcano.
Experience but unsymmetric.
Yeah.
But yet the only thing is to look into the literature, search for it.
How about the tremor? Maybe tremor can correlate with pressure or something like a change in the.
Yeah, the question is, I think, why? So apart from the, let's say, from the final result, which is of course important, this is going to the west. The west, which is so the part that is now active. Right?
Yeah.
Well, there is the new dome.
Yeah.
But this. So I mean, the question is why? First of all. So apart from the from the result, when will it collapse? For that, for the when, you can try to use something like failure forecast method. Failure forecast method has, let's say, you have to somehow fine tune it. So as I was saying, I wrote a paper, a review paper about that. But let's say let's make a resume of the method. So the method was actually proposed for landslides. So in the original method, the name does not come to my mind. It's a Japanese author. So he put let's say a model where you have an inclined plane, okay, a sediment, okay, and then a constant rain, okay, constant rain. This is the key point, the constant rain. So let's say the input is constant, it's not accelerated, and then okay, the rain comes down constantly, okay, but suddenly he measures the deformation of this sediment. And he finds out that there is an acceleration of the movement of this. And he uses this acceleration to compute, this, then he takes the inverse and it computes the time of failure. Then Barry Voigt took this idea and applied it to volcanoes. So he said, okay, we need a proxy for deformation, okay, or for this movement, okay. And he uses RSAM, okay, on the seismic data. But you actually have deformation, so you don't need a proxy. Okay? You can still, try to use the two things or combination of the two, but probably you need somehow to, because deformation of what with respect to what. That's, I think, is also important because you have several benchmarks, and I guess, if something is moving, it moves with respect to all the other benchmarks, basically. So you should understand, in which direction it is moving, and and if it is really constant. Because if you find some little, at least, acceleration, then you can use that to forecast the time. But the main question for me is why that part is moving, not the other. I guess it is the main reason is the instability of the flank. Yeah, and of course, on top of that, you have the building of a new dome, which of course, but so it is basically, yes, sliding down, which is so the normal thing expected in the sector. Yeah, but but the time is it's difficult. The only thing that I can. But what I was saying is that the original method of failure forecast, okay, at least for seismic data, then was adapted, fine-tuned with, for example, we can use just windows of 1 minute, okay, and computer some. But within this window, sometimes you have events, okay. The question is, should I take everything or should I throw away the events, okay? So one approach is to say, okay, I take everything, okay, because it's still the energy. Okay. The other approach is, okay, I throw away the events and I keep only the tremor, okay, and I use the acceleration on the tremor. But there is the opposite approach that says, okay, I don't care about the tremor. I care about the events. So I'm looking at the volcanic events, for example. Or, for example, the case of, I remember, Savage and Neuber, they focused on, because I showed the gliding lines, and the gliding lines was actually the acceleration of LP events, okay, of the number of LP events. So what they did was to apply a trigger procedure, extract the LP events, and compute the energy of only the LP events. So they computed they applied the idea of the FFM only to the energy released through LP. And maybe you can find some ideas to find maybe filtering somehow the deformation data or combining it with the seismic data, you can find this famous acceleration. So I think what you should look for is an acceleration of something that represents this movement. And then this you can use to forecast when it breaks.
Okay.
Okay, thank you.
Yeah, thank you very much. So maybe from the other audience, if you have insight or questions, I'll open the question for you. If no, I would like to have Agung. We talk about time series analysis and the way to relate this time series data with the events.
Yeah, thank you, Pak Wahid. Unfortunately, that our data is mostly not related with time series. Time series just the age, the dating, but it's not like this, I think. So I'm not sure about the growth of lava dome. It's related with the time series or no, but it's not a continuous measurement.
The growth of a lava dome is definitely a time series.
Yeah.
Why not? I mean, it's something. I mean, it's for example, I don't know, the height of the lava dome at a certain point as a function of time. So it's perfectly a time series. Don't see why.
Thank you. My name is Haryo. Together with Pak Agung and one person from PPTKG, we also works in the monitoring of the lava dome. But the thing is, because the Merapi is active, so the period of obtaining the data is getting more difficult. But the thing that we do related to the time series is to estimate the growth rate and then the geometry of the dome, and then to decide the critical point when it will collapse and form a pyroclastic flow. That's the case with the Merapi. But in terms of a general volcano, we actually really realizing that, as Pak Agung mentioned, we works on tephra, and the tephra, if we talk about the time series in tephra, we will get like step diagrams and to predict the future activity of a volcanoes based on the tephra. We usually do that, and even though it really expensive because the dating radiometric dating data is one of the highly cost in order to build the proper step diagrams for tephra. But another thing that actually I'm curious is about if we do time series analysis, but how to say this, but to make it more general, do you think it is possible, like do we really have no connection in terms of the volcanic activity in the same tectonic settings, for example along the arcs, and then we somehow we get similar data in Bromo. The caldera making is around 30,000, and then we also make another dating in Slamet. There is also an explosive event with no record at all, and it was dated around 30,000. And then another thing is in Sumbing. I remember it's around 20,000. We have another explosive one. Sumbing in Central Java is dominated with effusive eruption, but there is a single deposit of pyroclastic, and it's dated around 20,000. So in that kind of case, can we make a time series and try to understand, do we actually have like a busy period of volcanic activity in the same tectonic setting? Do you think that kind of application is worth to try, or it's just actually coincidence, pure coincidence?
Yeah, of course, you are talking about 20,000 years, 30,000 years. Okay, so it depends on the time scale you are looking at. I mean, if you are looking into million of years, then 20,000 and 30,000 are very close. Yeah, but otherwise they may be far away in time. Yeah, so it depends on your time scale. But going to, let's say, shorter time periods, of course, it is a time series. I mean, even anything that depends on time. So if you put the number of eruption as a function of time in a given area, it's time series. So there's no doubt. But for example, let's say in between 18th and 19th century, there was the eruption of Laki in Iceland. There was the eruption of Lanzarote, Montañas del Fuego, 18 something. There was an eruption in there was also another, I think, in the Azores Island, and also in Capo Verde, I think. Very close to each other, but always depends on on the time scales. So when you see Merapi and you say, okay, we have an eruption in 2010, and then an eruption in 2024. I don't know when this will be big. Yeah. Okay. So are they close or they are not close? Depend how far you are looking from. No. Okay. But But the Atlantic ridge in that period was all very active. That is my message. Okay. So, I fully agree that, it can be that, this part, but again, depends on the time scale you're looking at. Maybe between 20,000 and 30,000% years ago was very active. Okay, so all the area. On a short and even shorter time scales, in maybe few months, maybe I don't remember the year, but maybe 15 years ago, 15 years ago, more or less, there was a small collapse of Sciara del Fuoco on Stromboli, which caused a very small tsunami. There was an earthquake in Palermo. There was an eruption of Etna, and there was basically it was not a submarine eruption, but almost some submarine activity close to Panarea and other islands close to Stromboli. So we had in the same area of northern Sicily, let's say, 4 events in a few months. In that case, of course it can happen by chance, but I would be very, doubtful that it happened by chance. So there was actually an increase of general activity in the area. So it does not surprise me, and it perfectly makes sense.
So we have also Mbak Sulis here. She's doing master program in geophysics and working with SOMS, unsupervised. Yes, Pomrapi events classification. So perhaps Mbak Sulis can share also.
May I comment to Mas Aryo and also Pak Agung first before we move to another topics? Okay. So actually, I have many notes in my book. I'm sorry. I will jump around from one topic to another topic maybe. I'm sorry. Okay. Okay, from Pak Agung and also Mas Haryo that said they already work with TEPRA. So I just wondering whether we can do with the product of the volcanic eruption. Like as you know that our colleague in BPTKG is collecting the ash sample every eruption is happening or after the pyroclastic flow is happening. So I think this is the time series data also, but in the higher sampling rate, right? If seismic, we have the 100-second sampling rate, but for the ash analysis, for the ash sample or the rock sample, it is time series, but in the very higher sampling rate, right? We agree about that, okay? And then not regular actually, but in Merapi maybe every 4 years, like we talked yesterday. Okay, and then I remember when in 2017 I involved in with the college in Earth Observatory of Singapore. We work on the something like DNA-like prediction. So this is based on the biomedical DNA using the Sorensen algorithm. So every one of us have the DNA. I have DNA. Bu Nur Naning have DNA. You have DNA. So is the eruption. So is every volcano in the world. So maybe we apply the algorithm on the AirSam seismic data and also on the statistical seismic data. We try to see the DNA of the phreatic eruption. For example, phreatic eruption in 2012 is AABB, and then in 2013 is ABAB, something like that. So I think if we apply the same methodology on the sample maybe or the XRF or SAM analysis, maybe it can be something that we can get from that, I think. And then
Another thing is that, yeah, we know that tephra and also the rock is also origin from the volcano. See, it must be contain something, some information that we can know after we extract the information from that. We can extract the information from the seismic data. That is the contact, the sensor information that we put near the volcano. I think it's very maybe very promising in the near future if we use the catalog from the global maybe product of the geological product like tephra or the rock sample and the rock analysis. And okay.
Can I give a comment about that?
Okay.
So actually, we are also working on. So we have many collections of geochemical data that has major interest elements. So we actually tried to do K-means clustering analysis for those geochemical data to try to differentiate between arc magmas. So we tried that. So we tried that several times, and the answer to the tephra question that it is possible to do that. It depends on the parameters that we want to see. Whether we want to see the geochemical data or we want to see, for example, if we have tephra, we can actually see the proportion of glass or lithics or probably the shape or the bubble. So there are many variables that we can see, we can try to look at. So the question is, that is possible. So for example, Pak Agung and I, we work on we tried to use, so we built this PCA model, and we can actually, on top of the PCA model, we can build clustering analysis, either use K-means, and then we can build GMM model, Gaussian mixture model on top of it. And then we actually tried that on the some data, geochemical data from Sulawesi, and we also tried that data for the alkaline data in Java. And we also, we are now doing this along Sunda Arc data just to see the connection between tectonic setting and the geochemical product. So it's not exactly a time series, but there are many products which we don't know the age, the actual age of the product. We only know that these are the data coming from one volcano. So it is possible. It is very possible. And then as we do it, we find some challenges, like for example, like for this long arc Sunda Arc data. So we tried this PCA model, and then on top of the PCA, we did K-means clustering analysis, and then on top of that, we did GMM. And what we found that sometimes this unsupervised machine learning model is cannot exactly explain the pattern that we want to see. So this is the answer to that question, that it is possible, but also I have one other question for Pak Roberto. So do you have any suggestions on how to find the best model? So there are many, for example, like there are many factor analysis, clustering analysis model. So do you have any suggestions on which models that we can use for that that works best in our data? Because well, this is not exactly time series data. So we have very discrete samples with different values. So we try to look into this population, whether they show certain patterns or not. So do you have any suggestions on that?
Of course, there is no method that is, better than the others, no? So it depends really, you have to try different and see how they work. Also, I don't know if this is your case, but sometimes you don't know, when you perform a cluster analysis, for example, I was showing self-organizing maps, okay? Self-organizing maps, you have a self-organization of the map, and then you see that, some area behave similarly, okay? So they group, and so you need to cluster to determine, the colors, okay? But the question is how many colors? And that is a difficult question. I don't know in your case if you already know that you want to separate into 3 or 2 or 4. Yeah, do you know that?
So yeah, we tried that approach. So we know based on geological information, we kind of have guesstimated idea the cluster that we want. They want to be in how many clusters? Yeah.
So you have the number of clusters.
Yes, just for input.
4.
Yeah, no, not exactly, not 4. I think it was 4 or 5. I don't remember. Sorry.
Okay, but you have a number, yeah, because that's yeah, okay. Well, that's good. It's good in the sense that it is an additional problem is sometimes to determine how many clusters you know, because okay, and there are several methods to determine the number of clusters, to suggest you the number of clusters, but you apply them all, and most of the times they give you different suggestions. So clustering it's not easy, not necessarily easy. So yeah, you should try different methods and see how they work, and especially if you should somehow have some pre-knowledge where you are able, because to understand if one is working better than the other, okay, of course you have some mathematical measures that you can use, the difference within the cluster with the difference between the clusters, but in most of the time you have to decide which method is best on the base of also your knowledge of the specific field. Yeah? So sometimes you get a result mathematically, it is the perfect fit, but then you look at the results and say, well, this is not, does not make sense to me. Yeah.
So the best approach is try every model. Is that right?
And what you can also do is to use self-organizing maps first. So first you use, it depends also on the number of data that you have. Because, seismic data, we have, the problem of data reduction. We have too many data. We have to, to extract. But in geochemistry, for example, it's usually you have very few data.
Very cute, yes, very cute.
Yeah.
Very cute data. Probably just 3,000 around that data.
3,000.
3,000 data points, yes. Very
Well,
cute data.
Yeah.
Not so many.
Well, not so few. Okay. Yeah. So, one possibility is to first to build a feature vector, okay, what the same that you would use to do the cluster analysis, but first you use this data with a self-organizing map. It's an unsupervised method, so you don't need examples, you don't need to tell it anything before. Then, when you have the self-organizing maps, you cluster the nodes of the self-organizing maps, not your data, okay? And finally, you reapply the self-organizing map to your data, and so the self-organizing maps classifies, it goes to a node, and that node belongs to a cluster, okay? So, and in general, this procedure is can somehow get more abstraction, yeah? So maybe that could be, a way to try.
Yeah, that's a very good idea. We can try that. Thank you.
Before Mas Taufik, we want to know more about notes from
Okay.
Please, Mbak Sulis.
So we move a topic from the geological data to geophysical data again. So I remember about the Lombok earthquake, Lombok Island in the east of Bali. Lombok Island. It's there is an earthquake in 5 August of 2018, and then in 11 August of 2018, Merapi has the new lava dome. Okay. And there is the effusive eruption, and then I conduct some analysis with Pak Wiwit actually in my thesis, And then I get before the cluster before and also after the earthquake, there is some changing in the cluster. But actually, as the problem that you mentioned earlier, that we don't know when the changing of the cluster is ended. The earthquake is in 5 August and the explosion in 11 August. The distance 1,000? Yeah. 1,000, yeah. 7? Yes. 2018, yes. We have another experience with another earthquake actually. Please, could you put the microphone?
So if you take the tremor, you compute a number of parameters, okay, and you see the time evolution, okay, and you plot this time evolution, but you have to start, I don't know, 2017, for example. Okay. So you process 1 year and a half of data, okay, and then you superimpose on this plot the earthquakes, okay. Then you can see if some parameters change in correspondence of the earth. Of course, you have to process as long time series as possible, because of course, if you look only at that, it's difficult to understand if this is something that changes regularly. Okay. Then, of course, if you find that in correspondence of that earthquake, there is change of tremor that then led to the explosion, to the eruption, then of course it's kind of proof that this was the trigger. Usually, the earthquake, let's say, kind of give the trigger to a volcano that is basically ready to erupt. Okay, so Merapi was there, was ready to erupt. It would have erupted maybe in December 2018. Okay, then the earthquake arrives, it gives a kick, and then it starts a bit before that what was expected. Yeah. So I cannot believe in an earthquake that triggers an eruption that was not ready already. Different thing is the fact that the earthquake can change the tremor itself without causing anything big, but still the volcano reacts to that. And of course, if you find that many other earthquakes have caused changes in the tremor, okay, this is a good sign, this is a good evidence, because it means that the Merapi is sensible to the arrival of earthquake. Another thing that you can check is which earthquakes affect the tremor. Because, for example, at Popo, we did not analyze very long time series, but it was clear that there were earthquakes very close and or very energetic, and the volcano did not care. But other earthquakes, smaller or farther away, that influenced the volcano. So it can be linked, for example, from where the earthquake comes, etc. But yes, I would try to make a longer analysis to see if there is an influence in general of the earthquake on the volcano, and then if there is a change immediately after this, and then that causes, then you have a new regime of tremor that then leads to the eruption. Yeah. In that case, it's and then of course you can try to model, the stress propagation, blah blah blah. Right? That's another step. First, it is better to understand if there is a chance that it can influence.
Yeah, I think the changes in the tremor might be lead to the same kind of the triggering, whether this is the dynamic triggering or the static triggering from earthquake to the volcano, right? So the first thing that we can do, and then the easiest thing that we can do is to see whether the tremor is changing after the eruption, right? Yeah. Okay. Another question is about I know some people in INGV that doing the hazard assessment. Someone is Laura Sandri or Marzoki. Yeah, they are doing a lot of things in the hazard assessment using the Bayesian inference system. So we do the same thing in Merapi, but in the long term probability. So I think if machine learning can be the solution to the dynamic.
Let's say for internal using for assessment of hazard. Yeah.
For we use internally for the hazard assessment. So it's possible using machine learning to do it dynamically. So when the parameter is changing from the deformation, from the gas, from the temperature, from the air SAM maybe, and then it combine all of the parameter into the one maybe something like activity level, and then we can see whether this day the Merapi is quiet, and then the other day Merapi is in level 1 and Merapi in level 2 and something like that. So maybe it's quite practical for the monitoring agency like us if there is some available software in I believe in Vesuvius or in Etna. Thank you.
On Etna, well, Vesuvius is so quiet that he never moves from level 0. But Etna, yes, at INGV they use also. I don't think it is if it is published. I mean, on the web. I think it's kind of it is called something like activity index. That it takes into account the energy of the tremor, the number of earthquake, blah 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 blah. So I don't remember the details, but yes, they do have something like that. But that's a kind of internal decision of like summarize. It's also data reduction, yeah. But there is no machine learning involved in that. So it's just okay. You can write if the tremor is greater than this and the number of earthquakes is greater than that, then level 2. Okay. Yeah. But you can do also it, let's say in an automatic way. What I mean, if you are happy with the what your institute did in the last 10 years or so, okay. What you can do is to use a supervised machine, okay, where you give the examples, okay. So the input is R-sum is this, frequency content is that, frequency maximum is this, the number of earthquake is this, the deformation is this, the gas is this, the temperature is this, blah 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 blah, all the parameters that you have for 10 years, okay. And then the result is level 1, level 2, level 3, okay. So exactly, this is kind of tricky because this is one of the problem of supervised training, the fact that the examples that you give, the same happens with classifying seismic events, okay? Usually they are not classified all by, you give 1,000 events, but they are not classified by the same person, okay? And of course you classify different from him, okay? So that's the problem. During 10 years, the people that decided the level maybe have changed, but not so much because they were for many years. So probably he was the final, decision. took a final decision. So I think that's a good thing, to try. So just to take all the data that you can have. The important thing with machine learning is to have, so the feature vector must be all filled. So you cannot have missing data. So if for one period you don't have some data, you have to throw away that data. But in this case, it's not a problem because you have a lot of data. But I think this is a good idea, because then you can have a machine that tells you the level. And then of course you do not publish it automatically. You have to check, and because otherwise. Yeah, well, as much as you have. The more data you have, the better. Yeah. And because the level is changed once a day, or decided. No, it can be also more than once a day. Yeah. Okay. Yeah, but so you can take, for example, every day is a data point. Okay? So you build the feature vector, and so 10 years on 3,650 days. It's okay. Makes sense. And it's easy to do. The problem is to choose the parameter.
Still other notes? Okay. You said a lot of notes. Okay. Okay. Then Mas Taufik, you raise your hand. Maybe you have a comment.
Okay, thank you for your time. It is a very interesting topics, because I'm also a geophysicist and I'm applying machine learning for my ongoing final project this year, hopefully. So I want to bring back what you've said before in your previous presentation about you gave an analogy of how human train a machine by giving the data and the label. So you call that supervised learning. But in the case of unsupervised learning, we don't actually give the machine the data and the labels. So the machine learning by itself. But the question is, how do we know what the machine is learning? Because we don't know how the machine is learning. The difference is in the supervised learning, we know we gave an A, the machine learned the shape of A. We gave the B, the machine know how the B looks like, and the other letters. But in unsupervised learning, we don't know how the machine learnings. So we don't know how the machine would come with the prediction in a physical way or a mathematical way. So we don't actually know how it could be described in physics or mathematics, because we as geophysicists, we have to come up with physical explanations so our geologist fellowship could understand what is the basic event can be described physically. So my question is there any mathematical or physical way to extract the information of how the machine describes something, or learning something?
Of course, the problem that you mentioned is a very well-known one. Okay. In fact, one big field of investigation in machine learning is interpretability. So, to not only the machine in most of the times tells you, for example, green, okay, and you say what is green, but also you don't know why the machine said green, okay, which is another problem. So, to your question, I think there is no answer, in the sense that self-organizing maps, for example, will will tell you, okay, now we are in the green regime, okay, and there is no way to know from the self-organizing maps what is the meaning, the physical meaning of the green, okay. So you have to decide by yourself. For example, with examples like that, okay, we see that, you know, we had this green, then we had the red, and then we had the blue, and we had the explosion. So the green must be somehow some normal state, and then the red could be, you know, kind of, you know, unstable state that then leads to the explosion, which is blue. Okay. But the other question is also relevant, you know, how the machine decides that now we are in green, okay? And the important thing is to, to be able to ask the machine, how did you get this result? Because we are providing to the machine a lot of parameters. For example, I don't know, the amplitude, the maximum frequency, etc., etc. So it is important for us to understand if the machine decides for green instead of blue on the base of, for example, because it saw that the maximum frequency changed. And that for the machine is very important, okay? This is an important information that can go into the physical model. So then you say, okay, you know that the difference between green and blue is mainly not because of the change in amplitude, but because of the change in frequency content. And this can go into your reasoning to build your physical model. Okay. Then there is a full set of methods that I admit I do not know in detail, but they are exactly combining physical models with machine learning. So it's a combination of the two. So you are building together a physical model that uses machine learning combined. Okay, and I think they are called something like, well, there are several names, or something like physics-aware machine learning or something like that. But you should look also, you know, in the keyword interpretability of the results. Yeah, but this is very clear. So yeah, the fact that the machine says this, we are in these regimes, and another thing is, if we talk about tremor, we can analyze 10 years of data, okay, and then we can classify into, I don't know, 10 different colors, okay, and then we look. Actually, there is a paper that just came out in JGR, Journal of Geophysical Research. It was the first author is Sebastian Steinke. He's now in New Zealand. And he applied self-organizing maps, but then he applied a lot of post-processing, let's say, to get these regimes. But let's say that in 10 years of data you can get maybe 10 colors, okay, which represent 10 different regimes, and then you can see the time evolution of this, and then you can try to interpret these colors. But another thing is what happens if something new happens. So what is the response of the machine if it sees something which was never seen before, okay? And the machine usually, it does not say, I don't know, it gives you a color. So the most probable color for the machine, okay? So it still says blue, even if it is not so clear that it is blue. But blue is like il meno peggio in Italian, so the least worse, okay? Okay. But you can monitor this. You can monitor, for example, you can say, okay, each cluster has, for example, in my case, it was a spectral distribution, but it could be anything. It has a barycenter of the cluster, which is the most typical distribution of that cluster. And this you can also compare to the other cluster to see how they differ one from the other. Okay. But also you can use this barycenter to weight the let's say, the accuracy of the classification. So if the machine says blue and the vector, the feature vector in that moment is very close to the barycenter of the blue, you can say it is blue and it's really a typical blue. Okay? But if the machine says blue, but this vector in this moment is very far away from the barycenter of the blue, it means that the machine is basically assigned it the color blue because it had no other option, but it was not a typical blue. So maybe in that case, there is something going on that was never seen in your previous data that you used for the training. Okay? And of course, for volcanology, this is very important because you are seeing something that was never seen in the 10 years before. And this is usually worrying. Okay.
We have here staff from BMKG, Mas Yusuf with batik clothes. The head of the BMKG said that he want to ask, but he has another meeting. So he give the question to the Mas Yusuf. He's doing master here with me in the geophysics. And also the two. Please, Mas Yusuf, you have any comments?
Thank you. I have one question. Actually, for detecting the tremors is very complicated. But from the method you have presented before, it looks very the tremor can be detected clearly. My question, is there any noise or artifact on the detection process during the process? As far as I know, in the detecting process, there is always any artifact that include in the result. For example, if we use the threshold, something like threshold, when we lower the threshold, there is many event detected, but there is also many false alarm detected. Yeah, thank you.
Okay, so first of all, okay, we are not that, as I was said, so my principle is that the tremor is always there. Okay, so we are looking for specific phases or regimes of the tremor. Okay, so we want to know if the tremor changes, okay, if there are some typical regimes of behavior of the tremor, and when the signal to noise ratio is very bad, I mean, there is no signal without noise, okay? That's why I was, maybe you did not catch the joke, but, when I was talking about Takens says, okay, this can be mapped in the original dynamics, assumed with a simple hypothesis that there is no noise and the duration of the time series is infinite. Of course, in everyday life, we have, okay. So noise is always there. So we will never be able to remove the noise. But, so if the signal to noise ratio becomes too low, okay, so we have a lot of noise and a very little signal, what can happen is that the machine classifies in a regime, as I was saying before, so something that, this is blue because I have no other option, but you can get from the error, let's say the distance between the typical blue and your data that actually, this is just, because, okay. So in that case, you don't trust too much the classification. Of course, as the noise is always there, you can try to, not to remove the noise, but to decrease the amount of noise. So to increase the signal to noise ratio. And this is the example that I made for the infrasound data in Japan. Okay, so you can use, let's say, all these methods of, let's say, signal separation to determine different sources that can be nice sources, I mean volcanic or whatever, okay, but can in most of the cases be simply noise, okay. And then you are able to separate them. Of course, you have to recognize which is good and which is bad, but then you can, do other analysis to prove that, like in this case, for example, it was clear from Fakultas, but for example, if I separate into 5 independent sources, and then an earthquake arrives, and 3 of these sources react to this earthquake, and 2 of them do not react, most probably the 3 that reacts are volcanic and the other 2 are not. Okay? So you can, combine things, but noise, it will always be there.
So any other question? Okay.
Okay. First of all, my name is Aisha. I'm undergraduate student here. And my first question is, when we use data, extracted data such as temperature, humidity, wind, or something else, and we use it as an input node in a deep learning architecture such as artificial neural network, and how to know how many hidden layers in the system if we want to get a maximum accuracy and also minimum loss in the output. Because as I know right now, different prediction will give slightly different architecture layer. And my second question is, I'm really curious about your thought about the next improvement and research about AI in geophysics field, especially time series analysis. That's it.
Thank you very much. So the number of hidden layers, okay, is a good question. So in the, let's say, at the beginning, there was artificial neural network, okay. Artificial neural network had very few hidden layers, maybe 1, maybe 2. Okay. Why? Because when you increase the number of nodes, you increase the flexibility of the network, okay? So it is able to learn more things, but you increase, consequently, the number of weights of the nodes, which are actually the things that the network has to learn, to fix, to learn, okay? So, to train a network with many hidden layers, you need a lot of effort, because you need to find these millions of weights. Okay, so you need a lot of data, training data, and you need a lot of time. Okay, so theoretically, yes, if you increase the number of hidden nodes, then you get better results, but there is an effort. The main problem is, okay, apart from the, suppose that you have, in fact, a huge number of data, training data, etc., and you have, time, processing time. The other problem is the convergence. I mean, when you have a simple, if you have, 2 parameters to fix, okay, you can have a simple surface, okay, so you start from here and you go to the minimum, which is the optimal solution, okay. You start from here and you go to the minimum, very easy, okay. But if you have many parameters to fix, and here you have millions, you have very complicated curves with a lot of minima, okay. So you start from here and you get to the minimum here, but this is a local minimum. The real minimum is here, okay? And you will never be able to reach that, yeah? So not only you have to make, one training, you have to make many trainings starting from, from several distribution of weights, and then, somehow combine, throw away, and restart, etc. So it's a very complicated. So that's the key, message. So, the more ways you have, the more powerful the network is, but the more difficult it is to train. Okay. And the second, there are many methods that are coming out that can be combined. Also, now everybody is talking about ChatGPT. Okay, ChatGPT is a let's say, if you use it, it looks like something like magic. Okay, that it knows. You ask a question and then you get an answer. Okay, and it looks like he has learned the answer, but it is not like this. Okay, it is basically a processing tool for text. Okay, so when you use your phone in the last few years, okay, you are writing, I am going to, and then the telephone suggests cinema. Okay, this is the most probable for the machine. Okay, it is the most probable next word. Okay, what ChatGPT does is exactly this. So it starts from your prompt. Okay, and what is the next most probable word? Okay, and it gives a word, and then it adds this to your prompt, and then generates the next most probable, and then finally does like that. Of course, there is a random component, because otherwise it would answer always in the same way. Yeah, but more or less this is idea. So it does not understand what is going on. Okay, so there is no consciousness or nothing of the kind. Okay, but still, the approach is powerful. It can generate things that makes no sense. There are several examples of that on the net. But still, you can think, for example, of coding your data into an alphabet, okay, and then use this alphabet to generate words, okay, and then use these large machine, I don't remember the name, large text processing tools, like ChatGPT, to generate, answers, okay. So in that case, you can train it by giving words, and then, for example, the classification, volcanotectonic or whatever, okay, or rockfall. So that could be an approach, but there are really many different methods, and probably the key thing is to combine things together. In fact, now that in the last few days, there are many discussion about. I can't remember the name, but it is because there is I can't remember the name, but there is a website where you can use different machine learning model, and what they do is basically to use ChatGPT as a kind of human interface, okay, and then ChatGPT passes the data to all these models, machine learning models, and chooses basically the best answer so using different technologies. And that, I think, is a good way to go. So to combine the results of different methods.
Audience would like to make a comment or questions? Otherwise, we thank you very much, Roberto, for your very nice presentation and insight also, and you willing to share to us today for this great Italian Research Day. So
Thank you a lot.
Yes, no problem. Yeah, yeah. We thank also the embassy because it's believe we can do this event here in Jogja. So thank you very much. So give applause to Pak Roberto and thank you. I close this presentation and give to moderator.
Okay, thank you so much to Mr. Wiwit, and this is the last section to this discussion. I would like to thank you so much to our speaker today, Mr. Roberto Carnil, and the last we will hand over souvenir from Faculty of Mathematics and Science, Universitas Gadjah Mada, to our speaker, Mr. Roberto.
Now it's open.
Okay.
Thank you.
Finally, we come to the end of the event. I ask the Master of Ceremony are really sorry if there are mistakes in bringing this event. To close this event, let us close with prayer. May the events which we have to solve is beneficial for all of us. Pray, start. Amen. Thank you so much for your attending. Let me say goodbye. See you. Wassalamualaikum warahmatullahi wabarakatuh.